Hey everyone, today we are going to go ahead and continue our MyTorch implementation of a full deep learning framework. So as a quick recap, in our very first video, we implemented the array module, basically a array that toggles between NumPy and CuPy depending on if we're on CPU and GPU, that sort of stuff. We then, in the second video, wrote our tensor class. The tensor class is essentially what does the automatic differentiation that powers almost every modern deep learning framework out there today. And then in the third video, we wrote the modules. And the modules is like the NN.module. Anytime we do anything in PyTorch, we always inherit the NN.module into the class. And that NN.module is full of a bunch of just necessary operations, like moving things between devices, loading and saving weights, all that sort of stuff. So all of that, we kind of did that last time. That was essentially just boilerplate code. But now that we have this foundation set up, we have everything we need to start actually implementing the different modules. And our goal at the end of the video today will be to essentially build a tiny little BabyGPT model. And that will let us test the entire system that we've built, but we of course have some work cut out for us. The main thing is this. So as a quick prerequisite, as a really main prerequisite for a lot of this stuff, is I released a video a couple maybe months ago or maybe a month ago called the Auto-Gradless Transformer, where we implemented the entire transformer architecture with no PyTorch. It was basically just NumPy or CuPy. So that means for every single operation that you see here, linear layer, softmax, whatever, we implemented both the forward pass, right? How do you actually perform the function? But then the backward pass, how do we compute the gradients for that function for all of these different operators, linear layer, softmax, ReLU, embedding, so on and so forth. We will be doing kind of the same thing today. For every single method, like the linear layer, we're going to write the automatic differentiation method, and then we will write the manual differentiation method. We'll do this just so we can compare efficiency and stuff right at the very end. Now, while we're doing this, I'm not going to be doing any of the derivations of like what is the derivative of the linear layer, what's the derivative of layer normalization, that sort of stuff. The reason I won't be doing that is because I've already done all of those derivations in that previous video. So go ahead and take a look at that first. If you're confused about any of those derivations, we are just going to go ahead and just start implementing everything, right? We're just going to start implementing these layers in order. So let's go ahead and get started. So the first step is, if you remember in PyTorch, the way they typically structure PyTorch is there's functionals and modules. Like we have our function, or let's pull up nn.linear, right? So our standard linear layer in PyTorch, right? So here's our linear layer. You call it nothing fancy, but if you go to the source code for this, you're going to notice something in the linear layer. They use something called in the forward method f.linear, where you pass in an input, a weight, and a bias. And this is because the way that PyTorch works is you have a functional that actually does the thing, and then you have a module that essentially just wraps that function. So we're going to spend some time essentially just doing both. We're going to spend most of our time writing the functional, and then the module is just going to be a quick wrapper on that functional. So let's go ahead and get started with the linear layer just to set the stage here. So in functional, we're going to create a new folder here called layers. And then inside layers, we're going to create a new file called linear.py. Let's make this a little bit bigger. I'm also going to create inside the functional file, or inside the layers file, we're going to need an init for inheriting stuff. Let's make sure I paste this in. So these will be all of our inits. For now, we're just going to have the linear layer. The only ones we'll be implementing actually will be these layers for now. So I do have convolutions and stuff in my repo, but we don't need any of that for this. And the purpose of the sequence of tutorials is to do a language model. So we're going to be kind of focusing on language models specifically. So let's go ahead and start with the linear layer. In our functional, we do have a couple of, so let's go ahead and just set the structure up. In the functional, we also need an init.py, or not inside the layers, but inside the functional, init.py. There we go. So there we go. And in here, we're going to need a lot of the same things. I'm going to paste that in here right now. But for now, we don't need any of this because we're not going to be touching Triton. We don't need any of this because we're not touching that either. And we're going to need, well, we'll need all of this at some point or the other. But for now, let's just comment it out. We'll add them in as we go. And we're going to need the linear layer, but we're not going to need any of these. So these can go. Linear, we're going to need embedding and dropout, right? Drop out. So I'll just keep those here, but we don't have them just yet. So we'll implement that. Now, if you remember, the way that we set our thing up, our essentially our entire array system up was like this. So we're going to write one helper method, and then we'll get into the implementation of the linear layer. So the way we set this up was this. We can do import MyTorch, right, which is the package we've been writing. And we're going to do rand is mytorch.randn. And let's say we create a 2x3 tensor, and let's say the device is CUDA. Let's print out the rand. Well, if we do this, python test.py, we'll see it, this is the array that we just created, or the tensor we just created. Now, if we do rand.data, and actually let's do it this way. Let's do type rand, print type rand.data, and then print type rand.data.data. Just a couple of ways. So our rand, the thing we created, is a tensor. Inside each tensor, so inside the .data attribute, we have an array, right? We have the array. And inside the array, we have the corresponding CuPy array. As you can see CuPy here. The reason it's CuPy is because it's CUDA. If this was CPU, then it would just be a memory view. It's basically just our NumPy array, right? Just standard NumPy array. So there's a couple levels of essentially abstraction here, and we need to just be able to reach in and grab that data. So what we're going to do is inside the functional, we're going to create another file here called utils.py, and these are going to be very simple utils. We're going to do from array and from tensor, import tensor, and import array. Right, so we're going to import our array module or tensor module, that sort of stuff. So we're going to do def get inner array, right, to get the inner array, given an array. And if is instance, so this is going to be one level. So given basically a tensor, we want to return the inner array, and then the next one's going to be to return, one more level in. So we'll see that in just a second. So if is instance, array is, if it's already an array, then we can just return array, because that's what we want, right? This is the thing that's supposed to return the array type, right? The inner array, essentially. Our array, the one we built. If is instance, array, if it's a tensor, then we have to unpack it. So we're going to do if has adder array data. So if it has that .data attribute, which every tensor should, then we're going to return array.data. Else, we will raise an exception, right? That this tensor, for some random reason, or whatever we passed in this case tensor, does not have a .data attribute, which would not be good, but all tensors should have a .data attribute, so we should be fine. We're also going to write a def get inner array. So we want to go in 2 levels, essentially. This is also fine. If is instance. If we pass if array is a tensor, no problem. We can then do our array is going to be get inner. Just use the above method, right? Just a single unpack, just like that. And we're going to do if has adder array. So actually, just to make it a little bit more clear, let's put this back. It's not actually an array, it's going to be in .array. So there you go. You can see this is a numpy.nd array. CuPy.data will actually give the memory address, but or not CuPy, CUDA, sorry. There you go. It's a CuPy.nd array. So it's in the underscore array attribute, my bad. So because we have that, we can then go ahead. If it has it, we're good to go. We can return array.array. Else, again, just like before, for some reason this should not be raised because every array type should have a ._array module, because we wrote this, right? This is our setup, so it should always have it, but as a sanity check, it's there. Good. So these are just some quick helper methods. We're essentially just importing just for type hints, right? Okay, good. So now that we have that, I think we have everything we need for the linear layer. So in layers, we're going to be writing a couple of different layers today. We'll have a linear layer. We'll have the embedding layer, so embedding.py. And we will have our, let's see here, linear embedding, dropout, there you go, dropout.py. So these are the 3 layers we need. As kind of, these are the main linear layer, and then our embeddings, and then dropout are 3 core layers that we need for now. We'll work on the other ones after. So let's go ahead and set the structure up of how we implement each of these layers. So we're going to do import OS. This is going to be our linear layer. Linear layer. There we go, that's right. So import OS, import NumPy as NP, from MyTorch, import tensor, from MyTorch.nn.functional. And actually, these flags and things like that, we don't need to worry about it now. We'll need those later when we do our Triton stuff, so ignore that for now. So we'll come back and kind of add to these files later. From MyTorch.nn.utils, utils is not available just yet because NN is not importing them. So we need to quickly do right here. Let's make sure we get our imports all correct. So in this init right here, we have this is fine, okay? And then in functional, in its init, sorry, we're gonna have to do a little bit of work here. Oh, because I forgot the double underscore, rename underscore underscore. And we're going to have these, right? We just defined these, get inner array, get inner array. I think that should fix from mytorch.nn. Let's see here. In this init, maybe I should just go through and paste all my inits. This one makes it a little bit more annoying as we are building a package and there's always some package dependency that I'm missing somewhere or the other. So let's see here. I'm going to X out of all of the extra stuff. Just save it, it's fine. Get rid of you, get rid of you. Dot NN dot functional. Okay, so that's the problem. Functional does exist. So we're going to do layers, not layers, init. And then, okay, I see. Okay, so in layers and then linear, yes, we're going to do dot functional dot utils, my bad. So nn dot functional dot utils, there we go, my bad. We're going to import get inner array and get inner array, my bad. All right, good. So now that we have that, and I think everything else we're going to need at a later time. Now for our linear layers, let's just keep this in mind, how we set up a linear layer. Typically, basically y is going to be x at w transpose plus b, right? That's a standard linear layer. Now here's the thing about a linear layer. A linear layer can take in any number of features. So x has to be some, let's for now, let's just do a single dimension, batch by input features. W is going to be some output by input features. The reason it's output by input is because we're going to transpose it. This is because this is how PyTorch sets it up, right? So we're going to do a transpose here, so we need to do output by input. And then B is just going to be just a quick vector of size output, right? An output vector. And so that's the way that we will be setting this up. But alternatively, what if X had a bunch of extra dimensions, like A by B by B by C by I? Well, the way we do this operation is we first flatten it. We'll basically flatten all the initial dimensions, A by A times B times C. So all these get flattened together by I. And then we're going to map model it with a I by O matrix, right? Basically, again, we transpose the W. So to do this, we need to just kind of do a couple of helper methods. The first one's going to be def reshape for linear. We'll always have to make sure we reshape our data. So by default, reshaped is going to be false. We're going to do our dims. So basically all the dimensions, and then the last dimension in features is going to be x.shape. So this will essentially return a tuple of all the dimensions and then the last dimension, and that'll be our x.shape. And we can do if len dims is greater than 1. So if it's more than 1 dimension, then we have to flatten it, right? That basically means, again, I'll paste this little section in, right? If basically dims would be a by b by c, and then in features would be I. So because these 3 dimensions are greater than 1, that means we have a flattened to do. We'll do reshaped is true. And we can do if reshaped, then we can do x is x dot reshaped, np dot prod dims, right? We're basically just multiplying these 3 dimensions together by in features, return x dims and reshaped. That's it, right? It's just a quick helper method that takes some tensor, some, whatever, and then performs this reshape on it. And remember, this reshape is, we can do autograd through this reshape, right? Because we implemented in our tensor, right? In our tensor class right here, reshape, right? Reshape is a method that we can backpropagate through. So this is totally fine. So let's write the 2 methods. So first one's going to be def auto linear. And the auto linear is going to take some input, some weight, and some bias, by default is none, and other args, which are just basically there as a placeholder. In the same way, we're going to have a def manual linear. Input, weight, bias, none, again, args, pass. And later on, we won't be implementing this today, we're going to have a def fused linear. Input, weight, and sorry, there should be star args, input, weight, bias, activation function is none. We'll see all of this fun stuff later, right? This is where our Triton kernel will come up, and we'll work on that later. For now, we don't have to worry about any of them. We're just going to be working on these 2 today, and basically for every single method, we will have one of these later, just not today, so don't worry about it. So let's start with our auto linear. Auto linear is the easiest because autograd will take care of everything for us. We're going to do input dims are dims, and reshaped flag is going to be reshape for linear, and we're going to pass in our input, right? That's what this is going to do. Take some x, or take x, it's going to reshape our x, it's going to give us everything just as we need it. And this is going to be, sorry, not input dims, but inputs, my bad, input. And so given the input, the dimensions, and whether or not we reshaped, this will just tell us, do we need to unshape it? Because of course, we want to return the data back in the original shape, so we are going to have to like undo this reshape, and we'll see that a little bit later. So our out features, right? Well, how many out features do we have? It's going to be our weight dot shape 0, because remember our weight is, we transpose it, so it's going to be the weights again is going to be out features by in features, because we transpose it in just a second. So we're going to first do output is equal to input at weight dot transpose -1, -2. No problem. Dot transpose is a method we can backprop through. We implement that in tensor, and mapmul is another operation we can mapmul through, or we can backprop through because we implemented in the tensor. So that's our output. And we're going to do if bias is not none. No problem. Output is going to be output plus bias dot reshape 1, -1. Just add that extra dummy dimension in, because remember, this is going to basically the output here. It's going to be batch or whatever, but let's say just b by some output dimension. Our bias is just an output like this. So we're going to make it 1 by output here, and that will broadcast over that, right? Over the batch dimension, which is fine because again, our tensor class autograd can handle broadcasting. We've implemented all that. And lastly, if reshaped flag, right? If we reshaped it, then our output is going to be output dot reshape. Pass in those dims, basically reshape it back to all those dims, and then the output features. Return output. And the important part is, as we're defining these operations, every single thing we implement here has to be differentiable. Transposing is differentiable, mapmul is differentiable, adding is differentiable, broadcast sum is differentiable. Our reshape again is differentiable. So because all of these operations are differentiable, we can directly backprop through them using our backprop engine that we've already spent all this time writing up here, right? Good. So that's the first one. Now, this is technically fine, but also it's not exactly helpful, because sometimes for some operations, we don't need to backprop through everything. So this is the example I gave in the autograd video, where when we go ahead and define some function and we do a sequence of stuff to it, then we can technically each of these functions are differentiable, right? Multiply by -1, exponentiating, adding, dividing. We have all of these things written in our backprop in our tensor system, right? The autograd system. So we can backprop through this and it would be fine. But this is kind of a wasted compute, right? We'd have to kind of store first all of these nodes on the computational graph, and then we'd have to backprop through every single one of these nodes on that computational graph. We'd be better off doing something like this. This operation, multiplying by -1, exponentiating, adding 1, and then doing the reciprocal, this is just sigmoid. I know the derivative of sigmoid, right? I know the derivative of sigmoid is just the output times 1 minus the output. So I can manually define that gradient here just because I know what the output is. And this is much cheaper than doing all of this and chaining them together, right? So it's a little bit less important for linear because linear is such a simple operation that we're not really gaining anything by doing this, but it sets up the structure of what we will be doing for some of the other layers, right? So as a quick recap, remember that in our methods here, let's pick a good one. Let's pick maybe like the add method, right? It's backward. Here we go, add. So every single one of these methods was basically me performing some operation, right? So this is the actual forward pass, performing some operation. And then the backward pass was simply just writing the backpropagation, right? What is the formula for the backprop, right? And then wrapping all of that up in a tensor and then storing the add backward method right here so we can trigger the backward pass in our, well, backward method later on. So this was relatively straightforward. Now, what we want to do is instead of having this kind of structure for just a simple add, we want to write the same structure for our linear class. A good example was this little chunk of code right here. In sigmoid, we can either do auto, which is just like this, or we can go ahead and do the sigmoid function and then store the backward pass right here directly. So we don't have to backprop through all of this. I just provide the exact gradient information right here and then store that as my sigmoid backward method. This is then triggered during my backward pass. So this is what we're going to be using, basically setting up a structure like this for our manual methods. And the manual methods are preferable because they're a little bit cheaper, right? Saves us some of those, saves us on the entire topological sort and that sort of stuff. So let's go ahead and start this. So it's going to be our input, just like before, dims and reshaped flag is going to be that reshape for linear. Pass in our input, just like before. Our out features and in features is going to be weight.shape. Just store that right here. And what we're going to do first is our manual gradients don't need to do any auto grade. Like we don't need autograd anymore. So let's go ahead and grab the inner array. So basically, remember again, our tensor, inside a tensor is an array, like our array class that we wrote, inside which is like an NP or CuPy array. We don't need the tensor anymore. We don't need autograd anymore as we're manually defining the gradients here. So let's go ahead and just unwrap them. So our input array is going to be the get inner array input. And then our weight array is going to be simply our get inner array weight. And we can just go ahead and just transpose it right here, right? Transpose it right here, so we're good to go. If bias is not none, we can do our bias array is equal to get inner array bias, right? If we have a bias, then we can get that right there. Our output is np.mat mul input array weight array. And just as a quick recap, you might be wondering why NP, why not CP, why not CuPy.matmul? And that's because our array class, the array module, the stuff we spent all this time writing, right? All of this essentially will always use NumPy operations. The way I set it up, at least, is it'll always use a NumPy operation. But depending on the device, or depending on if the array we're applying it to is a NumPy or a CuPy operation, it'll dispatch it to the correct module class, right? So it'll dispatch it either to the NumPy version or to the CuPy version, just depending on where the device is. So that's where we can essentially just use NP everywhere, but NumPy internally, it's going to look at this array and it'll dispatch it to the correct one. So that's fine, right? Just a little shorthand essentially. If bias is not, I mean, we could also do it the other way. We just have to check the device every single time and say, oh, if it's CuPy, do cp.matmul. If it's NumPy, then do np.matmul. But this saves us some effort, right? If bias is not none, then output plus equals, we can just do an in place sum here, reshape 1, -1. And we can do if reshaped flag, no problem. Output is output.reshape dims and out features, right? So this is basically what we did earlier. We just unpacked it a little bit, right? Okay, good. So that's step 1. The next step is the backward pass. So we're going to define this as the linear backward grad output. So we're going to manually define the linear backward method here. So remember, our gradients are going to come in the shape of essentially, so let me paste this right here. Our gradients are going to come in the shape of some number of dimensions, right? There's going to be like A, B, C, and then O, or however many things were here. But we just did our operation in n by O, where so if this was like A, B, C, O, then A times B times C is equal to n. So n is equal to A times B times C. So we need to make sure we also flatten our grad output. Remember the gradients are always in the shape of the output. The output is in the shape, because we reshaped it back, to A times B times C. But we kind of need it in this form so we can do our matmulls. So let's go ahead and just flatten our gradient dimensions and then keep going. So we're going to do if reshaped flag. Right? So if we had done a reshape up here, then we need to also reshape our gradients, right, for the same reason. So it's going to be grad output is equal to grad output dot reshape -1 out features. So it's going to flatten everything by out features. So this will basically become an A times B times C, and A times B times C in our case is just n, right, just for simplicity. And we're going to do if weight dot requires grad. So is this something we need to compute gradients on? Well, if the weight, typically we want the gradients of the weight, this is going to be our grad W is np.matmul, the input array dot transpose grad output. So what we're seeing here is this is the upstream gradient to the linear layer. Let's pull that picture up right here. So let's say this is a linear layer, right? So this is x times w1, a, and then we have h times w2 plus b, right? So we have basically 2 different linear layers here. What I've just done is my grad output, this grad output here is my upstream gradient. So if I want to update this w, this h, or basically the gradient coming to this h, so dl dh, which is changed from dl dy, dy dc, dc dh. That basically dl dh is the upstream gradient. And the upstream gradient, grad output, is always in the shape of the output, because that's just more convenient to keep it that way. We went ahead and flattened it, and then we go ahead and compute the gradient with respect to w. I have the gradient from dl dh, but what I want is dl dw, right? That's what I want. And that's basically, this is the formula for it. So again, where this formula came from, I'm not going to talk about today because I've spent that whole video there implementing, right, and deriving these formulations. So I'm not going to be explaining these gradients because I've already derived them in those previous videos. So hopefully you already know them, right? But the gradient with respect to w is basically the matmul between our input array transpose and the grad output right here. Right, good. So, and just to make it clear, right, just to make this super clear, the input array, right, this input array right here is currently n by input. And the grad output is n by O, right, n by O. So I'm transposing this, so this becomes input by n. I can do the matmul. And once I matmul them, input by n times an n by O will just give a input by O. And then I can basically just transpose this again to give me finally O by input. And O by input is the shape of my weights, right? That's exactly my weight here, is output feature by input feature. So that's basically the operation happening. So we can do our if weight, and this is the key part, if weight dot grad. By default, when we initialize the weights, they're going to be initialized as none. Then we'll do weight.grad is equal to grad w.transpose, right? Go ahead and store that with that transpose. else, if it's not none, that means there's already some gradients there. And how PyTorch works is, again, it accumulates gradients. So every time you call dot backwards, it'll keep adding those gradients together. And so this could, if we called backwards a second time, it's no longer none. So we're just going to do our weight.grad plus equals grad w transpose. And once we're done with it, right, we don't need it anymore. Then we can do grad w is none, right? We can essentially just clear this variable. We're done with it. So that's just a little housekeeping. In the same way, we need the gradient, right? Linear layers are not just weights, they're also biases. We need the gradient with respect to the bias. Same thing. So it's going to be essentially if bias is not none, and bias dot requires grad. So if it's something that needs gradients and it's not none, then our grad bias is just equal to the grad output dot sum axis equals 0, right? That was the formula for it. And we're going to do if bias dot grad is none, then it's just same as before. We're going to do bias dot grad is grad b, and else bias dot grad plus equals grad b. Accumulate those gradients. Lastly, we need the derivative of the input to the output. So basically, we found derivative from dl to dh. We found the derivative from we have the derivative from dl to dh. We found the derivative from dl to db, dl to dw. We've computed those. But we also need dl to dx, because x could have come from something else, right? For example, h came from something else. So we needed the derivative of dl to this db, dl to this dw, but to continue backpropagating, we need dl dh. So we need the derivative of the loss with respect to the input of this function. And so we need to, and the input again is this input right here. So let's go ahead and do it. So it's going to be if input dot requires grad, we can do grad input is equal to np dot map mul grad output weight array dot transpose. That's the formula for it. And we can then do grad input is equal to grad input dot reshape dims in features. Just go ahead and put it back in the correct shape, because we did it. We basically are dealing with the flattened version, right? N by O, but we need to make sure that the gradients here match the shape of the input. And the input came in as A by B by C by O. So we want to make sure the grad input is also placed back into that shape. And then just like before, I'll go ahead and copy this in, so type it again. Just go ahead and store those gradients, and we are done. And now for the last part, requires grad. I'll just I'll paste the rest of this in because there's nothing interesting here. Tab this once. I think that should be good. Yep. So requires grad is if the input requires grad, or the weight requires grad, or bias is none and bias requires grad. So if at least one of these things need gradients, then we need to track gradients. And so then the requires grad is going to be, do we require grad? And that tensor.buildGraph enabled. We added this right at the end, but this was our context flag right here. So it allows us to do with MyTorch no grad, just like we could do in PyTorch, right? Just like we do in PyTorch. This is just a quick flag that will toggle the build graph method right here. And essentially every time we do it, we're going to check if build graph enabled. That method is implemented right here. Build graph enabled is it just checks this class class attribute of build graph. Is it true or is it false? If this is true, then we want to build the graph. If we don't want to, then we don't need to build a graph and we don't need to require gradient. Go ahead and store the output in a new tensor, which will have the requires grad flag, the grad function, right? So what is the actual function? This is the function. So it's going to be the linear backward if requires grad, else none. And then the function name, just so we can, visualize it later on. And of course, this method has three parents, right? This output was created from this input and the weight and bias. So these are the parents of this operation, and that essentially is it, right? Very, very simple. And so finally, we have our manual linear, we have our auto linear. So let's just write a generic linear method, which will again take an input, a weight, a bias is none, auto, right? Do we want to do auto or not? Auto is false by default. Fused is false, and act func is none. We do not care about these two things right now. So we'll just leave it in there and we'll come back to it later. We're going to do if auto then we're going to return, we'll just replace this method later, return auto linear, and it's going to take the input, the weight, and the bias. Else, we're going to return manual linear, the input, the weight, and the bias. And it's as simple as that, right? Nothing too crazy. We're going to be replacing all of this with the fused, once we have the fused one in there as well, then we're going to need these things. But for now, we don't really care. So let's give this a try. So we're going to do, let's say, mytorch.nn.functional.linear. Let's print this out. Let's see if the import works first. Yep, it's a function linear. So let's create a rand is mytorch.randend. We're going to have a, let's say, a 2x3 thing. And we're going to create a weight, and a bias. Let's say this has a 3 input. I guess it's output by input. So it's going to have a 10 output, 3 input, and the bias will just be 10, just like that. So we can then pass this into our linear. It'll take a rand, the input, weight, and the bias. Let's see if this just runs. Okay, good. So we're going to have an output. There we go. Oh, did I make a mistake somewhere? Return auto linear. Why did it return none? Oh, all of this needs to be tabbed out one. There we go. Yeah, needed to be tabbed out one. Let's just test that again. There we go. That's our output. We can see there's 10 values here, 2 by 10, because that's the output. Now, of course, all of this doesn't really matter if we don't set something like requires. Well, we don't need it for that one. The things that are really trainable, requires grad is true, and then requires grad is true. So now when we do our output, we'll see that we have a linear backward, because this can now trigger that output. So we can do output dot backward, and we can print w dot grad, and we can print out the bias dot grad. And there we go. We have our gradient information there as well. So nothing too crazy, right? Pretty straightforward. And that essentially sets us up for the linear layer. All right, so now that we've finished writing this linear layer, what we need to do is implement the module, right? So like I mentioned, every functional basically comes with its corresponding module, which is the way we'll be mostly using this stuff. So let's go ahead and implement that. So this is, again, pretty straightforward. In our modules, we're basically going to create a parallel set of stuff. We're going to go ahead and create our linear module right here. So new file, linear.py. And this should be relatively straightforward. So what we're going to do first is like this, make it smaller. So we're going to import math, import MyTorch. We're going to do from base module, import in that kind of the base module class, right? This is what we spent last video essentially making, right? Has all those important things in it. And we're going to do from very initial. We're going to import initializations. We actually haven't implemented that yet. So let's go ahead and we'll add that in just a second. We'll do import mytorch.nn.functional as f, right? So we're going to go ahead and use that. So what we're actually missing is one quick thing. Basically, when we initialize, so the module contains the parameters, right, that we want to train, and we need to be able to initialize, right? Initialize these parameters as whatever we want. So let's go ahead. I have this initializations here. I just never actually defined it. I am going to go ahead and copy paste all of this in because there's nothing interesting. Basically, initializations is just go ahead and initialize a 0. So we're going to use our zeros like method that we wrote, or ones like, or randn like, or rand like. So we have zeros, ones, if we want to initialize with normal, uniform, Xavier uniform, Xavier normal, Kaiming uniform, Kaiming normal, or we have kind of the in place. So these are essentially returning. These are just in place versions of them where we go ahead and do it this way. So basically the options are we can do like weight dot let's see. So we can, there's kind of two different ways we can do it. The main ones are essentially this. Let me go ahead and pull my example up. So the way we will do it is like going to be like init.uniform, and we'll pass in some weight, and this will go ahead and replace the weight, the data in here with the initialize, like uniformly initialized stuff using this logic. So that's in place. If it's not in place, then we actually return something, right? So it's just however you want to do it. I prefer in place method, so that's what you see here. And so there's nothing fancy in here. You can look at the method in my repo. It's just the different standard initialization methods that we have. But I won't go into too many details about these methods, because typically we just really care about like uniform or normal or something like that. So it's fine. We're going to keep it simple. Do I need to actually, let me just double check here. I don't believe so. I don't think there's any init. Oh yes, okay. So in this init right here, not that one, this one right here, we import initializations as init. So that makes it available to us, right? So we can easily import it. So we're just gonna keep this here. Nothing crazy. We just need that, and we won't worry about it. Other than that, just random initializations. That's all. And you could have built this in the method itself, but we'll need that later anyway. So we're also going to need from import initializations as init. Good. So class linear module. So this will go ahead and inherit all the stuff that we wrote again in our base module class. So in modules, we wrote the base module, and it has everything, right? Basically all the stuff we wrote, parameters, named parameters, all that fun stuff, right? So we are going to go ahead and do that here. Def init self in features, out features. We have bias is true, whether or not the layer has a bias, Auto is false. We want to use auto differentiation or manual differentiation, or later fused is false. We won't need any of these yet. Act func is none. Don't need either of these right now, but we will later. So I'm just going to stick them in here. Okay. Am I missing a comma somewhere? Let me double check here. No. Okay, good. Super dot init. That goes ahead and initializes our module, pulls in everything, and let's just go ahead and store all of these as our class variables, right? Again, we won't really need these yet, but that's fine. Let's go ahead and initialize a weight. So self.weight is going to be MyTorch dot, just initialize them as zeros for now. Zeros will go from out features to in features, and it's going to require scrad is true, right? This is something we want to compute gradients on. And the standard initialization for PyTorch linear layers is basically uniform between -k and k, where k is going to be math dot square root, right? The square root of 1 over in features. So this is how PyTorch initializes everything. So init dot uniform, and we'll do self dot weight from -k to k. So this is just using the initialization, one of our initialization methods. In this case, we're using this one right here. We provide a tensor, and we want it between low and high, right? So we're basically just doing uniform between low and high, whatever it's set to. In our case, it's from -k to k. Good. Now that we have that, similarly, if self.bias, then self.useBias is true, right? If we have it, then we want to use it. And we're going to initialize our bias in exactly the same way, nothing too crazy. Again, this is going to go from -k to k. Else, otherwise, self.useBias is false, and self.bias is none. Right? We'll store it like that. So again, def call self x return self.forward. Actually, so we just want to use the forward method. We technically don't need to do this because we already inherited it from here, and our base module already does this, but that's fine. We're just going to do it here again. Def forward. The actual forward method is pretty easy. It's just going to use our output is f dot linear, right? We already wrote this method, taking in x. Weight is self dot weight. Bias is self dot bias. Auto is self dot auto. What else was there? And then there was the other stuff. Fused is self.fuse, which isn't being used yet, and actfunc is self.actfunc. Neither of these are being used now. We'll just leave them in there. Return output. Good. So that is our very simple for method. Takes an input, returns it. Now, just for some helper methods, we need a repr, right? If we print this layer out, we're going to return, and I'm going to paste actually these in so I don't have to type these in. We have our repr, where if we print this layer out, this is what it's going to print out. And then extra repr is something we don't really need, and let's tab all of this back. Extra repr is not something we need right now, but when we print out the model, like the whole model, this is basically the important bit of information for this linear layer. So I'm just storing that right here as the important bit of information. This is used again in our base module, right? Extra repr. By default, it's none, but we can grab that extra information right here, and it's just used in this print function, which is not of any interest to anyone. So there we go. That's basically it. We've just gone ahead and this is essentially for every module we'll have an extra repr. It's just the important key information that we want for this specific layer. And that's basically it. So going back to our setup, if we go here, all of this is fine. We can now go to our test. So we had this test before. This was fine. Now what we're going to do is, instead of like this, we're going to do our layer is mytorch.nn.linear. And if we print out the layer, and this linear layer should take like 3 input, 10 output. Let's see if this works. Has no attribute linear. Looks like I'm missing an import somewhere. Let's find that. So this is in the linear layer. We have linear right here. Right. So in layers, we're gonna have to. There's always another init to include. So let's just add that in super quick. Right here in layers, new file, init.py, paste that in, and we don't need any of you, won't need you, and we only need that one right now. Everything else is not necessary. There we go. So it's a linear layer with in features of 3, out features of 10, bias is true. And we can just go ahead and do out is layer rand print out. Looks like we have a error. So unexpected argument fused. I guess that makes sense because we didn't actually implement fused. So let's just put these in here. Fused is false, and actfunc is none by default, just because we're not using these, but we will later. So we'll just keep it. There we go. There's our linear layer. Same deal as before, right? Same deal as before. We can now do, right, nothing really changed. Out.backward, and we can do print layer.weight.grad, right? So if we want to look at the weight layer, there you go. Those are my gradients for this specific weight layer, and that's it, right? Nothing else, nothing crazy. We've just done a quick wrapper on that linear layer. And this is kind of the pattern, right? So you get the pattern now. So let's go ahead and just quickly implement all the layers now. So we're going to basically do another layer here. We're going to do our dropout. So some of these will go pretty quickly. So dropout's pretty straightforward, just like before. It's going to be, all we need is from MyTorch, import tensor, and we're going to do def automatic differentiation dropout. Dropout is where you do input, dropout p, and training is true. So are we in training mode or evaluation mode? We're going to do if not training, or dropout p is 0.0, then there's nothing to do, right? If we're not dropping out anything, then we can just return input and we're done. Otherwise, we're going to have to create a mask, and this is going to be remember input.xp is just a shorthand to get, is this a numpy array or is it a cupy array? And xp is just my shorthand. It's just, what they recommend in the cupy documentation. So this is basically input.xp is either np if input is on if input is an NumPy array, or it's CP if input is a CuPy array. And we just want to access d.random sample input.data.shape greater than or equal to dropout p dot as type, and we want to make sure the type is the same, so we're going to do this. Quick check. So basically for every single position of the data, right? So input.data.shape. So for every single value in the data, every position, what we want to do is just randomly sample a value between 0 and 1 and see if it's greater than dropout p, and then cast it to the correct d type, and then copy is false. This is just shorthand. So when we cast something from a d type, if the d type is the same, like if we're trying to go from float 32 to float 32, then nothing will really happen and no copy is made. If we're going from float 32 to float 16, then a new copy of the data must be made in the new d type. So this is just a quick efficiency thing. Also, we have our ratio. It's going to be 1 over 1 minus dropout p. So if you recall, let me pull that up again, our dropout PyTorch. How dropout works in PyTorch is like this. Basically, randomly, right? We randomly zero some of the elements of the input tensor with probability of whatever set, and then the outputs, everything else, is scaled by 1 over 1 minus p, right? So this is basically to make sure that the variance of the data doesn't just randomly drop all the time, right? That wouldn't be very stable for training. So we're going to go ahead and just use essentially that, right? Just that exact setup. So we've gone ahead, we've selected which positions are going to be dropped out. We have our ratio based on the dropout p, and we can just do mask times equals ratio. Let's go ahead and multiply it, or mask is equal to, actually, yeah, this is fine, times equals ratio. So this is essentially just going to go ahead and scale all the positions. So this is Boolean, right? This is Boolean. So this is just a 0, 1 mask. All the 0 positions will stay 0, but all the 1 positions now get multiplied by that scale factor that we want to apply to the non-dropped out position. So this basically makes a 0 ratio mask, right? Whatever it may be. And we can then return input times mask. And this is essentially just 0, again, zeroes out the positions that were masked and then multiplies the unmasked positions by this specific ratio. And this will work out totally fine for our setup. Good. So that's one way to do it. Otherwise, we can do manual dropout, and I will go ahead and copy a bunch of this stuff because the initial part is identical. We don't really need to do manual here, as this is a really simple automatic differentiation, but it's fine. We're trying to stay consistent here. So if not training, right, same as before, go ahead and mask, multiply ratio, get the output data. Now our backward will be very simple. Our dropout backward. Again, we have our input grad, the upstream gradient. If input.requires grad, then our self grad is just the input grad times the mask, right? Because this is just a multiplication operation. We basically took data and multiplied by some mask. So the gradient, the upstream gradient, is just the upstream gradient times the values of that mask, right? That's basically that's basically it, right? We just multiplied by some constant called mask, and that's it. So we just had to make sure we multiply by that on the downstream gradient. This means that on our gradient, we scale it by the ratio for the positions that actually went forward, and we have 0 gradient information for the positions that were masked out, right? So the positions that were masked out don't contribute to the gradient, and that's basically what this is doing. And then everything else is the same as before. Input grad is none, accumulate, all that sort of stuff. And then everything else about the computational graph is the same, right? Go ahead and do it, convert back to a tensor. We have our dropout backward method, add parents, output, and we are done. And so our final dropout method was just using this if auto, then go ahead and pass it through there. If manual, pass it through there. Simple as that. So now we have this dropout method, and let's go ahead and do our module now. So new file, dropout.py. So our dropout module is very, very, very simple. Let's make sure we add it to the init. So right here, we're adding in a dropout now. So we're going to need that. And in this dropout method, it's very simple. So I'll just paste it in. We have our module, functional, and it's just a simple dropout method where we have the extra repr is the probability, the dropout is this, and we forward through like this, right? Enable dropout is if this module is in training mode Or if self.b is greater than 0, then we just pass it in and we are done, right? They're basically, again, using that functional method from before. Nothing too insane. Good. So that is another layer out of the way. Let's just X out of a bunch of these tabs, make it cleaner, easier for everyone to see what's going on. Up next is the embedding layer. This one's especially important, right, for our large language model. So let's go ahead and implement it. So we're going to need from MyTorch import tensor. We need from mytorch.nn.functional. Actually, we don't need any of that right now. We need from mytorch.nn.functional import, and then, functional.utils, import the get inner array, get inner array. We don't really care about inner array right now because that's what we'll need for Triton later on. Just for now, it's there, so don't worry about it. Def auto embedding indices. So remember, embedding layers take indexes and the weight layer, right? We have basically a vocab size by embedding dim weight matrix, and then we pass in some indexes like 1, 4, 6, 12, whatever, and each of these are going to index a row of this, right? So basically there's n, or vocab size, so we call this n elements in this, and each element has embedding dimension, dimensionality. And so this is basically saying grab the first thing along that along the row, the fourth thing, the sixth thing, so on and so forth. And that's all it is, right? So basically an embedding vector, and we're just indexing. That's all it is. And if we're indexing, well, then let's just index. We can return weight indices. And that's it. Right? It's just indexing. There's really nothing going on. There is no reason to write a manual gradient here, because this is just an index, right? The only thing this is doing is this is going to trigger in our tensor class, our get item. So our get item method, it's just going to directly trigger this. So if we did write a manual backward pass, it would be identical to this code, because this is the only thing we did, which means it doesn't really matter if we do anything else. So we're going to do def embedding indices weight fused is false. We're going to write a fused embedding layer later. That'll be I actually don't think it's any faster, but we're going to be writing a bunch of fused operations, Triton operations, so why not just do be as complete as possible. For now, we're just going to return auto embedding, and we're going to do our indices and weight, and that's it. Very, very, very simple. Now, of course, we need its corresponding module, so let's go ahead and uncomment U. So we're good to go. We've implemented all that. Let's go here in our layers. We need a embedding.py. We can go ahead and uncomment U, because we're about to implement that. And let's go ahead and do it. Embeddings are very, very simple. We can just paste it in, right? So we're just going to go ahead and import all the standard stuff. Embedding layers are typically initial. So we have basically every embedding layer is how many embeddings do we want by its dimensionality. Do we want to fuse one or not, which doesn't matter just yet. We again inherit that module class that we wrote. We have a repr, is just the embedding layer, or the extra, which is just the important information of the number of embeddings by the embedding dim. We have our forward method, just passing in the indices, the weights, and whether or not we want a fused thing. And we initialize the weights in the same way between minus k and k, just like we did. This is the standard PyTorch weight initialization for embedding layers. Of course, we can change this however we want in the future, but we are good to go right here. All right, good. So that kind of knocks out a couple of really important layers, right? So we have covered the linear layer, we've done our embedding layer, and we've done our dropout layer. So let's just start doing the other stuff. So layer normalization is probably the toughest one. Toughest in the sense that we're just going to implement it, so it's not going to be tough. But in the derivation that we did was probably the most challenging one in that video, in the autograd list video, right? So we're going to go ahead and implement that right here. Am I missing something? Embedding layers. There you go. Okay. X out, X out, X out. Okay, good. All right, let's pull this back up. Oh, my notes. Here we go. All right, so up next, this is going to be in a new folder altogether. So we're going to actually have, technically, we're going to have a couple of different types of normalizations. The ones we're going to focus on is layer normalization and later RMS normalization, as those are the two common ones for neural networks for LLM training. But of course, I also have a batch norm, group norm, and instance norm already in the Git repo, so you can look at those there if you're interested. We're going to create a new folder called norms. And let's go ahead and check our imports. We're going to do from norm, we're only going to need to import the layer norm for now, and RMS norm will just stay out. Okay, and this should be, sorry, not norms, but norm, singular. And this will also have an init.py, just like that. Sorry, I should have created the folder structure before I started, but we'll just go as we're going. And we're going to need you, layer norm. And so let's create the let's do LayerNorm.py. And yeah, okay, good. All right, layer norms. It's relatively easy. It's just the derivation is hard. So where the formulas came from, just go ahead and take a look there. I'm going to go ahead and do import numpy as np from MyTorch. From MyTorch, we're going to import in the tensor class. We need from mytorch.nn.functional.utils import the get inner array. Oh, cancel. Let me get inner array. So how does layer normalization work? Basically, you'll have let's say a batch by input size, whatever. And essentially every single one of these vectors, we have b of them, each of them having a length I. Each of the vectors of b of length I get normalized independently, right? So we basically just do a quick normalization of all of them. This also works out to be the same though if you have a by b by c by I, by c by I, no problem. We first are going to basically flatten these dimensions and basically say we have this many inputs. Each of these things have layer I. All of these things, a times b times c, worth of them are all normalized independently. And then we just go ahead and unnormalize them. So the initial part of this code, this kind of reshaping and unshaping, is identical, right? We did exactly this in the linear layer. We just need to flatten that dimension. So I can go ahead and paste that in, right? We already know that we have to do this to go ahead and reshape for layer norm. Exactly the same code. Let's go ahead and do the auto layer norm, def auto layer norm. Input weight bias EPS is 1E5, E5, and args. Now you might be wondering, I said normalization, where's the weight and bias coming from again? Remind yourself that, let me pull that up, torch layer norm. Here we go. Remind yourself in the torch layer norm, we have a normalization, so x minus its mean divided by the variance, right? The square root of the variance, so standard deviation. But we also have to multiply by, potentially, if we want, an element-wise affine. So do we want a multiply by some learnable parameters, and do we want to add some learnable parameters? This allows the model to kind of normalize it, but then skew it around a little bit, so it's not always stuck. So this is an optional input, but we do want to include them. And the hard part is basically the derivation, right, of the derivative, the backprop through all of this stuff. Okay, so to do this, what we are going to do is essentially, let's set it up. So again, input dims and reshape flag is going to be the reshape for layer norm input, just like that. And then our embed dim is equal to input.shape -1. And then let's go ahead and compute our variance. So variance x is input.var, dim is -1, because again, we're doing it along the last dimension. It's going to be basically, we have, after it's flattened, right, after it's flattened, it's basically just a n by I. And so we want to compute the variance for each one of these n things. where each of them have a length of I, right? An embedding dimension of I. So it's going to be a per row variance computation. Dot var, this is going to, and we're going to do keep dim is true, right? So we don't lose the dimensionality. So it'll be basically a n by 1 variance vector. And we're going to add a plus EPS right here. So that's the variance. And then we're going to do the norm. X is going to be the input minus the mean, which will be the same thing, input dot mean. Again, along the last dimension, keep dims is true. And then we're going to divide by the variance of x, square root, right? Square root of it. Now, you might be wondering, why are we able to do this? Can we differentiate through all of this? And yes, of course we can. We already wrote the backprop of the mean operation. We can see that right here with dimensionality and keep dims enabled. We already wrote the backprop of the variance operation, again, with the dim and keep dims enabled. So we have everything we need, right? We wrote all of we can backprop through all of these methods because it's just a variance operation, a subtraction, a mean, and a division. So we're good to go. Now for the extra parts, if weight, so if weight is not none, scale shifted x is going to be norm x, basically a norm line, times weight, the dot reshape 1, -1. So the weight vector is just a single vector of length I, right? Length I, but we have basically n by I, so we're adding that extra dimension here. We could have also done unsqueeze 0, as unsqueeze is a method we offer in our system. So if we have a weight, then we're going to do that. Otherwise, scale shifted x is just norm x. We don't do anything to it. If we have a bias, then our scale shifted x is going to be the scale shifted x plus bias, same reason, reshape 1 - 1. Just add that extra dummy dimension in. And if reshaped flag, normalization does not change the shape of the data, so we're just going to go ahead and do scale shifted x is scale shifted x dot reshape, and just go back to the dims by the embed dim, return our scale shifted x. And our AutoGrad will be able to backprop through all of this stuff, and we are good to go. Now what we're going to do is write the other version, right? The manual LayerNorm. So I'm going to go ahead and just kind of copy in all the stuff that didn't really change from before in the manual LayerNorm. First thing, we need to go ahead and grab the inner arrays if the weight or bias is available, right? So that's all fine. Yes. And yeah, embed dim because it's the last dimension, so that's good. And we're grab all this inner arrays, go ahead and compute the mean, the variance, the inverse standard deviation, and then go ahead and just do our x hat here. We're going to store x hat here because we're going to need x hat for the backward pass. We're going to need the values of this here for the backward pass operation. Scale if the weight is true. So if we have weight, then go ahead and multiply. Otherwise, it's fine. If we have a bias, go ahead and add the bias on, and then reshape back. And that's the forward pass. The backward pass, this is the derivation that was probably the most challenging because we have to differentiate through the normalization, which is challenging, right? It's pretty hard, but it's mostly just some algebraic manipulation, so it's not too bad. Grad output, right, or upstream gradient if reshaped flag, right? Just like we did for linear. The output data is the output gradient, or the upstream gradient, is in the same shape as the data, but we need to just flatten those initial dimensions if we had those. So just like we did for the linear layer, we're gonna just reshape it here as well. Grad output is our grad output dot reshape -1 by embed dim. If weight is not none, so if we have a weight, and if weight dot requires grad, so if it's something that requires gradient, then I will just paste the formulas in here, but these are the formulas that we essentially derived by hand. Remember that y is equal to x hat, right, which is our normalized data, times gamma plus beta. So dld gamma is dl dy, or upstream gradient, times dy d gamma. And so this is going to be our grad output, the upstream gradient, times dy d gamma, which is x hat, because what's the derivative of y with respect to gamma? Well, it's just x hat. It's the thing we multiplied by. And then we just sum up the gradients over the batch dimension because x hat has a batch dimension, but this gamma was broadcasted. Remember, this gamma is a vector of length. So we basically have a batch by I, and then gamma is just I, which means this gamma was broadcasted over all of the samples in the batch, which means in the backward pass, because this contributed to everything in the forward pass, we need to accumulate up all those contributions in the backward pass. So we're going to sum them up. So our grad gamma is equal to np.sum grad output times x hat, right? Grad output times x hat. And we're just going to sum them up along that first dimension. Axis is 0. Because again, we broadcasted it, so we need to accumulate up all those gradients. And that's our first one. No problem. Similarly, if bias is not none, again, the bias is the same setup, but here, the derivative of dy d beta, the bias is just 1. So really, it's just grad output times 1. So I'll paste that in right here. And this is, again, exactly the same thing as before. It's going to be grad output times 1 versus grad output. But again, the beta is a vector that was broadcasted over all the samples in the batch in x hat, which means in the forward pass, beta contributed to every single row of x hat. So in the backward pass, we need to accumulate up all those gradients. Again, sum. We're going to add it all together. And that's it. Now here's for the hardest one, the hardest derivative. This is the one that took us a while to derive, is this. We want the derivative of y with respect to x, not x hat, but x, right? So basically the pre-normalized data. So we need to backprop through normalization. And this is the formula that we derived to perform that, right? This is the formula. Where this came from, again, go take a look at that video because we essentially hand-derived all of this, and I don't want to do it again because it's kind of annoying. So we're going to do essentially dx hat. The derivative with respect to x hat is going to be grad output times the weight array, weight r, if weight r is not none, else grad output, right? So if it's not there, then it's just grad output. If it is there, then it's grad output times the weight array. Mean dx hat is np.mean dx hat, again, along that last dimension, and then keep dims is true. Our mean dx hat, x hat. So we have basically a mean computation, but then we also have a mean of a mean computation, which again, I don't want to go into too much, but mean is np.mean dx hat times x hat. Axis is -1, keep dims is true. And then grad input is going to be equal to the inverse standard deviation times dx hat minus mean dx hat minus x hat times mean dx hat. And I think I got all this correct. There's like nothing all that interesting about this. It's just an implementation of the formula. So you can see at the end, it's the inverse standard deviation, which we computed ahead of time, right? We computed that up here, inverse standard deviation, times the grad output times gamma. That's our dx hat. It's grad output times the weight array, or gamma, if it's available. Otherwise, it's just grad output, minus the mean of grad output times gamma. That's fine. That's this mean dx hat. It's mean of this, which is mean of this, minus the rest of this stuff, right? So it's going to be x hat times the mean of the grad output times the weight r times x hat, which we did right here, right? We computed that right here. Yeah, because dx hat is already the grad output times the weight array, grad output times weight array. So that's dx hat times an additional x hat term. And we go and average that up and store it, and we are done. That's our grad input. Again, we need to make sure we reshape our data back into the original shape before we actually add the gradients, but after that we're done. Right, that's basically it. So again, if any of this seems confusing to you, that's totally fine. Just go ahead and watch that video and it will make all sorts of sense. From that, we can just go ahead and same setup from before. Requires grad, wrap the tensor. The parents of this output is the input, the potential weight, the potential bias. And we are done. Okay, so this means our actual LayerNorm method is going to take an input, a weight, bias, EPS. We'll do 1E5 or 1E minus 5. Oh, did I actually double check? This should be 1E5. minus 5. Sorry, my bad. So 1e minus 5. Auto is false. Training, are we in training mode or evaluation mode? So training is true. And I think there was one other thing. We don't really care about the training mode right now. This is going to be needed when we do the fused operations later. And fused is false. Why we need it, you'll see, but for now it's fine. If auto, we're going to do return auto LayerNorm input weight bias EPS, right? I think that's everything we had. Input weight bias EPS. Yeah, input weight bias EPS. Else, it's going to be the return manual LayerNorm of the same things. Input weight bias EPS. And we are done with the layer normalization. So we imported it right here. And let's go ahead and write the module in exactly the same way. So we have norm. We're going to need the init.py. Let's populate that first. So this is going to be norm init.py. This is going to be simply from .LayerNorm, and we need to actually implement LayerNorm.py. And this is pretty easy. So yeah, we'll just walk through this. So it's, you don't have to type all of it. So again, LayerNorm inherit our module. It's all the stuff that we talked about just earlier. And then we're going to go ahead and just store some stuff, right? What's the total shape? What's the embedding dimension? All that sort of stuff, right? So we're good to go. We have, and okay, the way this actually works out and the way PyTorch does it. So we're trying to follow the PyTorch syntax as much as possible. LayerNorm. In layer normalization, what you do is you provide the normalized shape, right? Where the D dimensions, where D is the dimension of the normalized shape, right? So that's the dimensionality. And basically a normalized shape is supposed to be an int, a list, or a torshot size, whatever it may be. And we're essentially just saying how many elements are we going to be normalized over. And by default, if a single integer is used, it's treated as a singleton list, and this module will normalize over the last dimension, which is expected to be that specific size. So for example, if our data, like standard transformer data, will be batch by 256, token size by 768, then LayerNorm, we just pass in 768 because we want to normalize over this 768 dimension. If you put something else like 500, then this will no longer work. Okay? So that's it. So we're basically checking for that, grab the embedding dimensions based on that normalized size. And then we'll initialize our weights and biases. And by default, our weight will be 1. We assume a 1, and then we assume a bias of 0. And that's the standard weight initialization scheme for layer normalization. Weight of 0, bias of 1, and we're good to go. In our forward method, go ahead and just do a quick sanity check. And this is just making sure that the dimensionality we passed in for normalized shape actually matches the data. And so basically, if the number of dimensions in our normalized shape doesn't equal the actual normalized shape, then we have expecting trailing dimensions to be normalized shape, but got this shape. So this is just a shape check that we can actually normalize with the dimension we gave, but we really don't care about these complex setups. We just pass in 768 because we're only going to be normalizing over 1 dimension when we use it, so it's fine. We get the original shape, the number of dimensions. We go ahead and do that quick reshape right here. We do it right here. We could have also used our other, we also did it right here, right? Using this reshape for LayerNorm, this would have also done the same thing. So that's fine. We can do it in either place. Go ahead. We use our existing layer normalization that we already implemented with all the methods. And then we just reshape it back to the original data if we need to. And then we return. And we are done, right? And then we have the repr and extra repr, same as always. So there's nothing too different about this, just a couple of more operations. So we have now completed our layer normalization. Let's go ahead and deal with our activation function. And then we'll do softmax and then cross entropy, and then we should be done, right? Because we don't have to do any of this stuff because multi-head attention and feedforward are going to be composites of the other operations. So we'll be able to just use our autograd system for this one right here. Let's go ahead and do ReLU next, right? We could also do GLU, but we'll do ReLU today just to keep it simple. So this is going to require us to do a activation. So in our functional, we're going to create a new folder called activations. And again, in activations, we're going to have our init file. There are a bunch of activations that we can technically have. As you can see, we are going to focus on essentially these couple, maybe GLU as well. So let's maybe keep, you know what, we'll keep all of them. We'll probably end up implementing all of them later. But for today, we just need from.ReLU, import ReLU. We just need the ReLU. And of course, from.softmax, import softmax. There's some confidence design. So these are the two we're going to implement right now. Let's go ahead and implement the ReLU.py. And we're also going to need softmax.py. Okay, ReLU first. ReLU is super easy, so that's where we're going to start with it. So we're going to do import numpy as np, import from MyTorch, import tensor, and then we're going to do from mytorch.nn.functional.utils import get inner array, get inner array, def auto ReLU input. So ReLU functions are very simple. It's basically just going to be 0 if the value of the element in the tensor is less than 0, and it's just the same when it's greater. So we basically just multiply everything less than 0 by 0. Simple as that. So we just need to create a mask, just like we did for Dropout. This is going to be a mask. It's going to be a tensor where np.where input.data less than 0. So wherever it's 0, we want it to be 0. Otherwise, we want it to be 1. And we're going to make sure np.where input.data less than 0. There we go. List of parentheses. There. And we want to make sure it's dot as type input.btype input, and then copy is false. Just go ahead, basically create the mask, create our tensor, and then there's our mask, and then we simply just return input times mask, and that should technically be enough as ReLUs. Again, just a very simple operation is we're just multiplying our data by this mask. That's 0 where the values are less than 0, and then 1 where the values are greater than 0. And it's as simple as that. Our manual ReLU is not really worth for me to type out. It's exactly the same thing, right? Go get our inner array, grab the mask, and then we can just do a quick in-place assignment here. So basically input array, wherever our input array is true, wherever it's less than 0, just go ahead and set it to 0. In-place replacement is faster, as we don't have to create new memory allocations for the outputs, right? We can just reuse that memory allocation. These little optimizations actually add up to quite a bit of a speed up later on, and we'll kind of see that when we're doing the Triton stuff. Backward pass, exactly the same thing. The output grad, wherever we multiplied by 0, then the output gradient will have 0, right? Because that's what we multiplied by. So again, in place assignment, just multiply by the gradients. If it was zeroed out in the forward pass, then the gradients at those elements will be zeroed out in the backward pass. And everything else is the same, right? Everything else is identical. We just go ahead and save it and we're done. So that's our ReLU. We can then, again, just go ahead, and I'm toggling back and forth here, but let's just stay in order. In activations, we're going to create a new file in our modules. We'll create the nn.ReLU essentially. This is going to be right here in it. We need you, and we will need you, just not yet. So we'll get there. So in our ReLU method, let's go ahead and implement that. ReLU.py. This is very simple. It's just that, right? Just go ahead and use the ReLU method. And auto infused or false right now because we haven't really wrote any of that yet. So actually, something I forgot, we need to write the actual ReLU method, right? We didn't do that here. So let's go ahead and do that real quick. It's just this. Oh, we don't need all of this complication right now. Else return manual ReLU input. And there we go, right? So that's using our ReLU. We don't care about fused right now. And we are good to go. Let's X out of, let's save you, X, remove all of these extra imports. Okay, good. So ReLU's done, very simple. Similarly, we can do the softmax, right? Softmax function. So to do softmax, again, softmax is a slightly complicated, derivative, but we do that implementation in the video, right? So you can go watch it there. So import numpy as np. Again, we need import from MyTorch import. You can see this is very just repetitive, right? Implementing every one of these methods just gets a little bit repetitive, but you got to do it, otherwise they won't be there. So auto softmax x, and then dim is by default -1. And here's the key part: we want to make sure we do softmax, but the stable softmax, right? So instead of just doing softmax, so remember softmax was basically e to the power x divided by some e to the power j, right? Basically just, that's our standard softmax formula. But what we're going to do is e to the power x minus the max, and e to the power j minus the max. And this helps stabilize softmax, as this essentially just makes sure that we're always exponentiating something that's 0 or less, right? It's just a linear shift of the data, but the linear shift of the data doesn't affect the values of the softmax. You get the same output at the end, but it makes sure that we're not exponentiating like e to the power 100, because that would break our like float 32 precision or something like that. So step 1 is basically max x is going to be x.max, which is a differentiable function. We wrote that method. Dim is dim, right? And then keep dims is true. And then we're going to do x shifted is x minus max x, no problem. And then we have exponentiating it. Expx is x shifted dot exp. Go ahead and exponentiate everything. Then sum exp is going to be exp x dot sum dim equals dim. Keep dims is true, and then we can return expx divided by sum exp, and we're done. So that's our automatic differentiation for softmax. Similarly, manual softmax. We're going to do x, and dim is -1. And all this initial stuff is the same, so we can paste this in, right? The forward pass doesn't change. Again, we just grab that inner array and then do that same set of operations. It's just backpropping through all of this is quite a bit of effort when I know the formula for the backprop. So def softmax backward, grad output, so that's our upstream gradient. If x dot requires grad, so if we need to compute gradients, so we're going to do our softmax. Remember the softmax derivative, the derivative is going to be s times grad minus some grad times s. So this is the non-Jacobian form of the derivative, right? So this is essentially, again, I have a whole video where we derive all this. You can go take a look at that, but we're just going to implement it blindly here. We're going to do sum grad s is going to be np dot sum. That basically we're doing this piece right here, np dot sum grad output times out data axis equals, along whichever dimension we did the softmax on, and keep dims is true. And then our grad input, basically the grad is going to be, or grad input, it's fine. Grad input is going to be out data times, so s in this case is the output of the softmax. So that's out data, the output of the softmax. Out data times our grad output, the upstream gradient, minus the sum grad s that we just did right there. Everything after that is identical, right? Go ahead and accumulate those gradients in, and then go ahead and store with the softmax backward, right? So that's your softmax method. So we can then go ahead and do our actual def softmax. Again, x will have a dim by default, -1. Auto is false, and later we're going to write a fused operation to make this even faster. If auto, we're going to return auto softmax x dim equals dim. Else, we're going to do return manual softmax x dim equals dim. We don't really care about the other stuff again. Good, so that's basically it. That is our softmax method. Again, we can go back to our manual or our modules and just put that in there. Very, very, very simple. Let's make sure the init got you there. The init, we can uncomment you and make a new one, new file, softmax.py. And there we go, standard softmax method, right? We're just a module that wraps it. We actually probably use it as the functional method, but this is, just to match PyTorch as close as possible. So now that we have softmax, once we've done linear, softmax, we've done an activation, embedding, LayerNorm, dropout, all that's left is cross entropy loss. So let's go ahead and do this last one. So let's, so we're going to create one more here in our functionals, and this one's going to be losses. There's all sorts of losses, right? I mean, PyTorch has an entire laundry list of losses. The only one we really need for LLM training, at least, will be the cross entropy loss. So let's go ahead and do that. Activation, new file, or no, sorry, in functional, we're going to create a new folder called losses. In here again, init.py. In this init.py, all we need is cross entropy loss, as that's all we're implementing today. And then we're going to do cross entropy .py. I spelled this wrong. Let me rename that. Entropy. There we go. Okay, good. Now, for the cross entropy, I have a little bit of a caveat. I have had unstable gradients when using the automatic method to do cross entropy. I'm not exactly sure why, and I haven't been able to chase down the issue just yet. So we're just going to go ahead and do the manual pass for cross entropy and call it a day, right? Because I don't want to really dig into that. So we're going to import numpy as np. We're going to need, again, we're going to write a fused cross entropy that's going to be way faster later on. So we don't really care about any of this. This is just to set the stage, right? Functional.utils import get inner array, get inner array. So we're going to do a def auto cross entropy, but I've had issues with this, right? So we're just going to raise a not implemented error if we try to use this. Def manual cross entropy. Again, we have the formula, but this takes logits. And the logits are in the shape of like the batch size by num classes, right? So C. And then for each of those samples, we have a index, so targets. Basically, we'll have a vector index like this. What is the target? What's the correct answer? Ignore index is -100. So we have our ignore index, of course, which is don't compute loss on this specific sample, which is fine. Like if we're masking or something like that, we have the ignore index. By default, it's -100 in PyTorch. And then we're going to do just whatever. And so we're going to do dims. Num classes is going to be logits.shape, and then flattened dim is np.prod dims, right? Because we can pass in data as like batch by, like we could have A by B by, like before, A by B by num classes, right? C is num classes. So we just need to make sure we flatten all those together, dims, get the total dimension. And our logits data is going to be get inner array logits, and we're going to reshape flatten dim num classes. And here is one key thing. We want to make sure that whatever we're doing here is in float 32 precision. This doesn't matter now, as our training is all will be happening in float 32 precision. But when we start dropping to float 16, this starts to get a little bit funky, right? So we want to avoid that and keep the precision high enough so we don't get overflows or underflows when doing the rest of these operations. I'm going to go ahead and copy the rest of this little piece here, right? So there we go. That's our setup. Now we're going to go ahead and do our couple of small things. So we got our logits. Yes, we have our logits data. I don't actually need this line. There we go. Yeah, mistake. I can delete that in my actual code. And then we have our targets data, right? So we have our targets data. Good. So first step is we need a mask. So in our targets, the samples we don't want to compute the loss on will be indicated with -100. So like if the targets are like 2, 4, 1, 5, -100, 2, 3, 5, -100, we only want to compute the loss on these terms, and we want to ignore it on these two, which means if there's 1, 2, 3, 4, 5, 6, 7, 8, what is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 things in this list. When we take the average, we only want to take the average over these 7 because these two are not supposed to be counted. And so we need to do a couple things. First one's going to be, let's just make a quick math. Targets data does not equal to ignore index. So just make a true false. And then valid counts. So how many valid samples do we have? That's going to be mask.sum. That's it. Okay, now what we want to do is go ahead and compute our cross entropy. So let's remind ourselves real quick that cross entropy formula. Let me pull it up real quick. We have cross entropy PyTorch and then cross entropy loss. Here we go. So there are extra stuff we could do like label smoothing and all that, but we're not going to deal with any of that right now. Cross entropy is pretty straightforward. Basically what we need to do is take raw logits. We need to compute our essentially this softmax, or we need to compute the softmax, and then on the softmax we need to go ahead and compute our loss, right? So this is going to be essentially the same setup as before. We need to compute the softmax, then compute the loss, and we'll be good to go. So let's just start with one thing. We need the log sum exp per row because we need to essentially get that denominator of the softmax. That's right here. So this is going to be stable log sum exp per row, right? Along the logits dimension, right? Number of classes dimension. So logits max is going to be np.max logits data. Axis is 1 because we are assuming it's 2 dimensions at this point because we flattened it. And then keep dims is true. And then exp shifted is going to be our logits data minus our logits max. And then this is exactly what we did in softmax, right? Nothing new. And then np.exp, we're just going to exponentiate it right here. And then we need our log sum exp is going to be np.log np.sum exp shifted axis is equal to 1, keep dims is true, plus logits max. So all we've done is basically make sure that we did a stable exponentiation here, but then once we take the log, we basically had this extra logits max term that we subtracted inside the exponentiation. The exponentiation got removed once we logged it, and so we're adding it back to shift the data back. So this is just a stable way of doing log sum exp, exactly like how we did it before. This is again implemented in that autograd list transformer where we kind of do exactly this, nothing different. Now that we have that, what we have here is the log sum exp of every single class for every single sample. So now what we need is the negative log likelihood only for valid rows, because some of these rows are invalid, right? Because we have a -100 mask. So what we're going to do is our negative log likelihood is going to be the log sum exp dot flatten, right? Dot flatten minus logits data, and it's going to be np.arange flattened dim targets data. So what we've done here is, remember, this log sum exp, after we did this sum, basically, well, okay, so just to be clear, we had some n by c, right, number of classes. This log sum exp is computed per row. So basically, log sum exp is an n vector, right? It's basically a vector of n, 1 per sample. And now what we want to do is compute the log sum exp minus the minus the correct, what do you call it? So let's maybe draw this out real quick, or put it right here. Let's say we have 2, 7, 5, 1, 1, whatever. Like this is what we have. And let's say the correct answer here was 0, the correct answer here was 2, the correct answer here was 1. So what we've done is for every single one of these samples, right, every sample, we've computed the log sum exp. We have that right here. But then what we have is we want the logit, right, the logit for the correct answer, which in this case, 0 is going to be this one right here, 2 is going to be this one right here, 1 is going to be this one right here by the index. So that's what we're doing. Basically for every single sample in the batch dimension, right, whatever n is, go ahead and grab the correct, grab the logit of the correct target data. So that's going to be like 0, grab the 0th index, 2, grab the second index, 1, grab the first index, so on and so forth. The reason we're again doing this is we've essentially just rewritten all of this stuff here. Notice that we essentially have a log of something divided by something, right? Well, that's fine. We can just do log of the numerator minus log of the denominator. But there's actually a negative sign in the front, so it's really the log of this denominator minus the log of the exponentiated numerator. And log of the exponentiated numerator is just, well, just x, right? And that's basically what it is. So that's a simple manipulation that we go over. So we're doing, let's just make this clear. Negative log, and then we have e to the power x divided by sum e to the power like j or whatever. And so this is really just the same as saying negative log of this, and let's put the negative sign around all of it, minus log sum of this. And this log sum exp is exactly what we computed up here. It's a per sample computation. But we have this negative sign here, so we can actually flip it. We can say this. So this one gets the negative, and we do plus right here, or in the way that we wrote it, it would really just be this one minus this one, which is fine. And log of e to the x is just, well, it's just x, right, the logit. And what we want is log of e to the x for the correct answer, right? For the correct answer. That's what we want, right? So that's the key idea. We want log of we want the logit of the correct answer, and that basically gets us exactly here, right? We have our log sum exp minus the x, the logits of the correct answer. So it's just a little bit of algebraic manipulation, but this is fine. And then our loss value, right? This is again per sample. We've computed the negative log likelihood per sample. So the loss value is going to be equal to np.sum NLL divided by only the valid counts, right? Because we're dividing by however many samples we actually have. All the other ones are essentially being ignored, right? Okay, good. So I think, let me double check here, mass.sum, valid.counts, and we are good to go. That's it, right? That's nothing too crazy. We can make sure this is, okay, yes. All right, and once we've done that, we want to make sure we cast our loss to the correct D type. Just make sure it's the same D type as logit. So if we're training in float 32, it doesn't really matter because this will all be in float 32. But if we're training in float 16, our loss will be computed. All of this will be computed in float 32. We'll cast it back to float 16 once we're done, which we don't care about right now, but keep in mind for later. Entropy backward, grad output. So the all we need for the backward method for cross entropy is pretty simple. Logits.requires grad, right? If this thing requires grad, no problem. Softmax is going to be exp shifted divided. So just compute the softmax again. np.sum exp shifted. Axis is 1. Keep dims is true, right? Go ahead and recompute our softmax values. And then we need to initialize the gradients. So our grad input is going to be softmax dot create a copy of it. And our grad input is equal to np.arange, or grad input is input in the positions of np.arange, flatten dim, and then our targets data, we're going to do minus equals 1, because that's basically the derivative of our this entire operation. The derivative of cross entropy is softmax minus 1 for the correct answers and minus 0 for the incorrect answers. And that's it. That's the derivative of cross entropy. Again, how we got there is in that video. Of course, that's not enough because we also scaled by, we also took an average, right? So we scaled by this valid counts, right? We scaled by valid counts. We had to do the same thing here. So grad input is equal to, or we can do times equals to, grad output divided by valid counts. Now, one thing we have to keep in mind is what is grad output? It's the upstream gradient. But is there anything more upstream than the loss? No, there isn't. This is just 1. So this is basically just going to be 1, and that's it. It may be something that isn't 1 when we do dynamic loss scaling for mixed precision compute, but for now, it's just 1. As far as we're concerned, this is 1. So we're just scaling by 1 over valid counts, because that's what we multiplied by here. We multiplied by 1 over valid counts. So we're multiplying our gradients also by 1 over valid counts to make it the same. And then our grad input times equals mass.reshape, 1, -1. We want to make sure for all the samples that are invalid, right? All the samples that are invalid, because they had a ignore index of -100, those samples should not be contributing to the gradient. So we're going to zero out those gradients as the mask identifies which samples are, 1 for contributes or 0 does not contribute. So that's how we're managing that. No contribution to the gradient. Lastly, grad input is equal to grad input, dot reshape. Just put it back in the original logic, whatever the logit shape was, and make sure it's the correct dtype. Logits.dtype, copy equals false. And then the rest of this is identical. So we can paste the rest of it. Oh, did I not import tensor? From MyTorch, import tensor. There we go. So that is our cross entropy loss. Again, add the gradients on, and then there's our loss basically, our standard loss computation. Store everything in the tensor and return, and we have everything we need for backprop. And so lastly, we can do def cross entropy logits targets ignore index is -100. We're going to include something called a soft cap later. I'm just not going to include it right now as we don't really care. And then fused is false because we don't have that right now. And for now, we're going to do return manual cross entropy logits targets ignore index, and that's it. That's all we care about right now because everything else is for the fused operation, which we'll get later. Okay, good. So that handles our cross entropy. So I think that covers all of the different layers. Of course, layers are not the only thing we need. We also need an optimizer. We could do SGD or Adam. We will be doing AdamW today, as that's the optimizer we're going to use for our tiny little baby model and our 1 billion parameter LLM way in the future when we actually get to that point. So to implement optimizers, first I have init. Oh, of course, wait, before I do the optimizer, I need to wrap up the second part. We need the module, right? We need our module. So we have our functional module losses. Let's go ahead and add that in as well. So we're going to do module and then modules losses. Here we go, init. So we just implemented this one. So module groups, or not module groups, losses, new file, init.py. There we go. And we're going to add in cross entropy.py. And this is pretty straightforward. It's just going to use, it's just a wrapper, right? So cross entropy, just take logits and targets, pass it through. We don't have soft cap or anything right now, so we can ignore that, right? We don't need to worry about any of that right now. Okay, good. Now we're done. Now onto the optimizer. So let's X out of everything. X out, X out, X out, X out. Okay, good. So let's close stuff. Make this a little bit neater. So as we saw, we have functional and its parallel set of modules. in these modules, we want to make sure some of this stuff is available. So we have this is available, so we're good. Let's make sure our imports are good. So inside modules, we have another init. Okay, this one's good to go. In functional, we have an init. We want to add stuff in here. So this should be valid, but not MSE loss because we didn't implement that. We haven't done that. We have from activations, from .activations, we're just going to import in ReLU for now because that's the N and Softmax. That's all we've done. Everything else are not stuff that we have done yet. Stuff we'll do, but we're not there yet. All right, I think we're good. So we'll check on import errors later when we get there. But for now, let's implement the next part. Alongside NN, we also have to implement our set of optimizers. So we're going to call this optim, or not inside NN. Should be up one more. Move. There we go. Optim. So optimizers, very simple. It's just going to contain optimizers, right? So we're going to do new file, new folder, optimizers.py, or not .py. Let me delete that file. My bad. Delete. Okay, we need a new folder. Optimizer, and we need a second folder. Let me think. Oh no, actually no, we don't need to do extra folders. We're just going to put it all in one for simplicity today. Okay, so we're going to do optimizers dot py. Yeah. Okay, and we also need an init, new file, init. There we go. From optimizers, import everything. All right, so we need to implement an optimizer. So optimizers are kind of passed in like this. So we're going to be following the same PyTorch setup where essentially we're going to have params. So normally we just do AdamW and then model.parameters or whatever. But we can technically have multiple different parameters. Like different parameters could have different settings, like the weight decay, learning rate, that sort of stuff. So this is the weight dict, right? It's a weight dictionary. And we can just basically do it that way. So that's how we're going to do it. Import MyTorch. I think that's all we need. So let's define the base optimizer. So class optimizer. And this is just what are the things the optimizer needs to be able to do. So first step, of course, a optimizer needs to be able to write, update. So raise not implemented error, def 0 grad self. Raise not implemented error, def init optimizer state. So how do we initialize the optimizer? This doesn't matter as much right now. It doesn't matter for like standard stochastic gradient descent. It matters for Adam though. So we're going to need that as well. Raise not implemented error. We need def state dict. So remember, when we train neural networks, and we're checkpointing our neural network, there's kind of a couple things we need to checkpoint. Of course, we need to checkpoint the model and its parameters, but the optimizer also has a state, and that needs to be checkpointed as well. So we're going to implement a state dict here that stores those temporary values so we can resume from checkpoint, essentially. Def load state, self, pass, and here we're going to return none by default if there isn't anything. Load state, just do nothing essentially, if unless specified. Def update learning rate, self learning rate. So this is just a method that can take a learning rate and just update it. So we're going to do if has adder self param groups, right? So if there's param groups, then we have to simply do for group in self dot param groups, like I mentioned, right? So we can have multiple parameter groups. We'll do group update the learning rate to learning rate. If we don't have param groups, then we can do elif has adder self learning rate, then self.lr learning rate is learning rate. That's how we're going to do it. And then def repr self raise not implemented error. So we haven't done that. So this is just the base, right? The base optimizer. Nothing crazy. It just has all the methods that we're going to need to do. Now in my Git repo, I've implemented SGD and Adam and AdamW. I am just going to do AdamW today, as that's the only one we need going forward, right? So, but everything kind of looks the same, right? So once you do one of them, you've kind of done all of them. Class AdamW. This is an optimizer. Def init self parameters parameters learning rate. Let's just set the PyTorch default 0.001. Beta 1 is 0.9. Beta 2 is 0.999. EPS is 1e -8. And weight decay is 0.01 by default. Weight decay is 0.01. So what makes Atom different? So there's Atom with weight decay, and then there's AdamW with weight decay. And basically what makes AdamW different is it's identical to Atom, but it uses decoupled weight decays. And I'll show you what that looks like in a bit. So we're going to do if is instance parameters. If we passed in a list or a tuple of parameters, that means we have basically different parameter groups. So what we're going to do is if is instance parameters. Just check the first thing in the list is a dictionary, right? Then basically that sets it up, right? That is a parameter group. So we can do self.paramGroups is an empty list, and we can do for group in parameters, just a loop through each of those parameter groups. Again, let me just pull this up as a reference, like this, right? We have different parameter groups here, so we just want to load each one of those individually. Okay, so to do that, we're going to do for group in parameters, param group is equal to just a dictionary of params. And this is going to be param, basically P, for P in group params, right? We're looking inside here, this model.embedding.parameters, like we implemented the .parameters module, or basically method, it's a generator, right? So we basically loop through them right here. P for P in group.parameters. If P dot requires grad. No need to have non-gradient things in here, right? Everything else is kind of the same, so we can go ahead and just paste this in. And what we do here is the reason we're using .get is if I don't provide a learning rate here, then I'll use the default learning rate. So .get basically checks, oh, is this there? It's not there. Okay, use the defaults. So basically that's the fallback value if it's not directly provided. And we can then do self.paramGroups.append param group, right? Just go ahead and for every single one of them, append them on. Otherwise, if it's not a list, then it's just a single param group, in which case we can just do this, just store, again, in the shape of, in the same way we did here, it'd be a param group with just one group, right? Just one thing in here, and that's it. Okay, good. So I'm going to put a comment on that one, so when you run it later, it doesn't throw an error. We need a device. So I assume, right, this is just assumption, and I think it's fair, that if one of the parameters, or basically all the parameters, whether they be in multiple groups or they be in one group, regardless, every single parameter in everything, so it's like the embeddings, the transformers, and the head, everything is on the same device. That's fair. It would be weird to have like some of these parameters on one device and then like another parameter on the CPU. If we were doing tensor parallel, where the model sharded between GPUs, then yes, this would no longer work. But I am not going that complicated. We're going to end at DDP essentially, because for a 1 billion parameter model, we don't need a tensor parallel. So device is self.paramGroups 0, right? So look at the first param group, look in the params method, look at the very first tensor, and just grab its device right there. So we're going to assume that all the parameters are on the same device, even if in multiple groups. And then we're going to do self.init optimizer state device. Now the important part, let's write that method, optimizer state. What we're going to do is we need to create the states for our Atom. So every optimizer is obviously a little bit different, but Atom is pretty well defined. So if I look up the AdamW from PyTorch, you'll see that Atom has, along with its parameters, we need to essentially initialize a M0, the first moment, and V0, the second moment, right? And of course, V0 max as well. So we need to initialize this stuff just so we can follow this formulation, right? Follow this formulation. So let's go ahead and do that. We're going to do for group in self.paramGroups. In addition to all the information we already stored in the param groups, we're just going to add on some additional stuff. First, group M is going to be MyTorch.zeros like P device equals device. dot data for p in group params. So basically all I'm doing is, and this should be self and then device. What I'm doing is I'm looping through every single parameter in this specific group, creating a 0 tensor, initialize as zeros, for that parameter, make sure it's on the correct device. But these are tensors, and I don't really need it as a tensor. I just need the raw value. So I'm just going to do dot data to get it as the array, right? So this will be our own array class that we've implemented internally. Because tensors are really just good for AutoGrad. There's no AutoGrad here. We're just doing some computation, so we don't really need the tensor. So we can simplify our life by just accessing the array module internally instead. In the same way, everything else is the same. So we're going to initialize our v, our t for our bias correction, and then we have our beta 1 and beta 2 as well. So again, this is all just based on the formulation right here. Right, so we have a beta 1 and beta 2 power. We'll see all of that come, but basically it's this little t right here. Beta 1 to the t, beta 2 to the t, that sort of stuff. So let's go ahead and just start implementing the standard step. So this is the important part, right? Def step. So every time we initialize an optimizer, it'll load the parameters and then initialize this stuff as well. This is what makes Adam a little bit more expensive of an optimizer, because not only do we have to store the parameters, but we have to store 2 more copies of zeros essentially for those parameters, right? For the second and first and second moments. So step self. It's going to be pretty straightforward. So this is exactly going to follow that formulation from PyTorch, right? I could do a video on like the derivations for Adam, but it's probably a little bit less interesting, so we won't do that right now. For group, so for every single group, our group t plus equals 1, so you've done an iteration. Group beta 1 pow, right? So power is times equals group beta 1, and then group beta 2 pow times equals group beta 2. So this is how we're going to essentially just basically starts at 1, and then we just keep multiplying by this over and over again, because remember, we're doing to the power t, right? To the power t. So basically every step we're just multiplying beta 1 to itself again and again and again, or beta 2 to itself over and over again. So we start at 1 and we just start multiplying and we are good to go. So after that, our learning rate t, this is going to be our group learning rate times 1 minus group beta 2 power to the power exponent or square root of it, 0.5, divided by 1 minus, so I'll just actually make sure I'm typing this correctly, it's just this. So basically our bias corrected learning rate is, it's the existing learning rate times 1 over the second power square root divided by the first power. And that again comes from right here. Let's see. Data moment, we update. Oh, right here, right? So basically it's v over that. So yeah, that's all it is. So it's just following this again. Okay, that's the learning rate t. And then we can do for I, p, and enumerate group param. So for every single one of these parameters, we now need to update it. If p dot requires grad, which should be true because we've already pre-filtered it for things that require grad, we're going to do g is p dot grad. So p dot grad contains the gradient information, right? That's basically our these deltas right here. We have the gradient information. So now that we have the gradient information, we can go ahead and do the update step, which is just going to be our gamma times our lambda learning rate times theta, right? So, or actually gamma's learning rate and gamma's our lambda is our weight decay and gamma is our learning rate. There we go. Sorry, misspoke. Okay, so first group m I times equals group beta 1. So this is our update biased first moment estimate. So I'll actually paste this in, right? So basically take our, for this specific moment, the first moment, for the ith tensor, because we're looping through all the parameters, so for the ith parameter, multiply it by this, right? This is our update of our first moment estimate, as you can see right here. M is going to be essentially first multiply and then add to it. So what you see here is first multiply and then add to it. First multiply by, so beta t is beta 1 times mt plus 1 minus beta t times gt. So we have first beta 1 times mt, so that's that, and then we're going to add 1 minus beta 1 times our gradient, which is exactly what you see here, right? Not too crazy. We're again, exact same thing. We're going to have our second moment estimate, which follows the same formulation, but now because it's the second moment, it'll be times the gradient squared, right? Gradient squared right here. And then what we're going to do is essentially set up our denominator. The denominator is going to be the, it's going to be this right here. We're going to do square root of the v plus epsilon. And so let's go ahead and do that first. So our denominator is equal to group v I for the ith parameter, square root, right? So 0.5 plus group whatever the EPS we selected was. That's our denominator. And our step size is equal to the learning rate t times the group m I divided by the denominator, right? So that's the final step size that we want. So going back right here, right? So we want the learning rate times the steps. So we've kind of computed all of this, right? We have everything we need. We have our step size, we have our moment. All we need to do is multiply it by the actual learning rate that we have right here. That's what we've just done. So it's a learning rate times the group m divided by this denominator. That's our step size. And so what we can do now is in place, we can do our p.data minus equals step size, right? Just go ahead and push our data in that direction. That's our parameter update. And now what we can do is a decoupled weight decay. It's decoupled because we essentially just do it separately. We're going to now do our weight decay directly on the parameter. And the way we do this is this update rule right here, right? Theta t is going to be minus gamma lambda theta t minus 1. So we can go ahead and do that right here as well. We're going to do if group weight decay does not equal to 0.0, so if it's not 0, then we're going to do p.data is equal to p.data minus group learning rate. What is the learning rate for the group? Times group weight decay times p.data. And that is our essentially just weight decay penalty, right? We're adding a small penalty of if the weights get too large, then this becomes a larger penalty essentially. And that's it, right? That's our entire update. So that's our decoupled weight decay update. Def 0 grad, let's step back one, def 0 grad self for group in self.param groups. What we're going to do is for p in group params, instead of setting the grad to zeros, we're going to do p.grad is just none, right? Just basically clear it out of memory. So it just saves us some memory essentially. Okay, now for more housekeeping stuff. So I can go ahead and just paste these in because it's a little bit less interesting. It's just unwrapping what we have here. So the state dictionary for this is going to be the state and the param groups, right? Basically the param groups being the we'll see it. So for every single group, what we're going to do is we're going to have all the m's and our v's. We're going to have the t that we're at, the what beta are we currently at, because of course, as we're training, right, as we're training our model, these values, the m's and v's, t's, beta 1, pow, beta 2, these are all going to change, right? They're going to update and become some like meaningful value that's helping to smooth out the gradients, because that's what Adam does. That may be true, but if we stop training and start again, we need to initialize these weights. Like we need to basically pick up these from where we left off, because if these start from some random place or basically start from scratch again, then the model will essentially diverge training right at the beginning, because it's already through training has a good estimate of the momentum, right? The first and second order momentums If we start training over and don't initialize this correctly, then it's lost that estimate and it needs to essentially recompute it again. But by the time it's done that, your model might have not trained as well. It could have diverged. Something bad could have happened. So we need to make sure that we just can go ahead and initialize our optimizer exactly where it left off. So we have your state dict for every single one of them. Let's just store this stuff, right? This is the group state. We have the MVT beta 1 and beta 2. That's what we need. So our state dict, inside the state, we can go ahead and store this group state. And then the group dict, right, tells me, this group tells me that what is the learning rate, beta 1, beta 2, EPS weight dict. Basically, what were the settings? What are the settings of this specific group, right? So these are the things that we've iteratively stored and computed by training. And these are the things that we set ahead of time, right? That's basically how we define the Adam model, right? Based on whatever we set it up here. So basically for every single group, we're going to go ahead and store the group's state and a dictionary of just information about that state. And that's basically it. So this is something we'll need to checkpoint. In the exact same way, we need to be able to load, right? Load this state. So given exactly the same thing, we just need to load it. There's nothing fancy in here. We need to make sure first that if we saved a optimizer with 3 groups, then when we load the optimizer, the loaded optimizer, like it should be the same, right? Nothing should have changed. If something changes, then this is not going to work because we can't load back into something that's different. And we can do for I, group state, enumerate. So for every single one of them, just go ahead and just store them, right? Just copy everything back in, copy them back in, store them, and then we are good to go. So this is basically just initializing everything. We created these param groups here, and we created our extra kind of information right here. Then when we initialize, just go ahead and load them and replace them. Just copy everything back over, and that's all that's happening. There's nothing fancy in here. It'd be good to just be able to print. This is just a fancy repr. So that's why we need a numpy at the top, just so we can print it out. Import numpy as np. It's just a fancy repr that will print out, like, you know, some information about the model, like how many parameters there are, how many parameter groups there are, that sort of stuff. So nothing interesting in here. The main part is this, right? This is really the algorithms, like bread and butter, right? So you just want to keep an eye on this. But again, we didn't really do much. We just followed everything that essentially was described right here, right? Good. So we now have everything. We have a, going back here, we have all of our layers, and we have an optimizer. And I believe that's enough for us to train a baby little GPT model. So let's start giving this a try. We're going to create a folder outside of MyTorch. And I'm going to call this, let's see, I'm going to call this BabyGPT, just like I have. And in this, we're going to have to implement a model.py and a train.py and a utils.py, right? So we'll be training this will be just like the Nano GPT. We'll be training it on the Shakespeare data. So let's go ahead and start with that. This code, again, is directly from the, it's fine. Let's just go ahead and write it, right? So we're going to do def, we need import requests, and we need import numpy as np. So we just need some data first, right? So if we need data, we also need a tokenizer and that sort of stuff. So I'm going to go ahead and just paste this initial part right here. Print all text, and let's just print out the first 100 tokens. Python, we're going to do BabyGPT utils.py, and we need to do prep Shakespeare. There we go. So that's the first 100 characters, essentially, of this specific data set. Right, so the first thing we need to do is just tokenize it. We're doing a simple character level model. So cars is sorted list set all text. Give me all the unique characters in this data set. And vocab size is going to be len cars, right? So however many, I think there's 65 in here. So we can quickly print that out, right? So if we run this now, you'll see we have, these are all the characters, and there's 65 possible characters that we can pick from. We can do quick tokenization, right? Just storing some dictionaries, car to index, index to car. Basically just loop through and give every single print car to index, give every single letter or token a special, unique index. So this can take text and convert to numbers, and then index require is just opposite, right? It takes numbers and converts them back to text. And we'll need that when we actually generate something, right? We can write a quick encode method. Given a string, all it does is return car to index C for C and S. So basically just go ahead and index or tokenize everything. Our train test split is pretty straightforward. I want to leave 10% for testing purposes. So there you go. Basically keep the first 10% or the last 10% for training, and then the first 10% for evaluation. So yeah, nothing fancy. We're just splitting the text and just grabbing 10% for training, 90% for training, 10% for testing. Now that we have that, we can go ahead and encode everything using this quick encode method. And so we will quickly see here that we have cart to index. Oh, this is a dictionary, so it should be like this, my bad. We can see there's 1 million tokens for training, about 100,000 tokens for validation, no problem. And we can just go ahead and store some of this information, right? So in meta, we'll have the vocab size, and the 2 tokenizers, right? So that's everything we need. We're going to convert this to a training data, right? So a NumPy array, and then a validation will be another NumPy array. And we can then return our train IDs, val IDs, and meta, right? Now this is basically just one long vector, right? One long vector of indexes. We need to be able to grab random samples from the data, right? So we can do import random, and what we're going to do is def sample array, and num tokens is 256. So how many tokens, consecutive tokens, do we want to grab? So because this is standard GPT, I'm not going to go into the super details of GPT. I assume you already know how to implement a GPT. What we're going to need is basically, the idea is if let's say we want 6 tokens. That means we're going to have 0, 1, 2, 3, 4, 5 as the input, and then 1, 2, 3, 4, 5, 6. So basically we want 0 to predict 1, 1 to predict 2, 2 to predict 3, 3, 4, 4, 5, 5, 6. That's the pattern, which means what we really need to index is not 6 tokens, but 7 of them, and then keep the first part for input, and then the output is this part right here. So the num tokens we really want, num tokens, is going to be num tokens plus 1. We need an extra 1 for the next token prediction. If len array, this should be the case for us, is less than num sample, num tokens. Oh, sorry, no, not num tokens, num samples. If we don't have enough, we can raise a value error. That shouldn't be the case for us, but that's fine. Start is going to be random dot rand int 0 to len array minus num samples, right? So just however it is, and then chunk is going to be the array from start to start plus num samples. And so if we and then our x or input is basically, like I mentioned, chunk. It's going to be everything except for the last thing, and then y is the chunk, first thing to the end, and we can return x and y. And this will go ahead and just randomly sample a single sequence, essentially, from our array, right? Just like we have here. Good. So that is our utils, nothing too crazy. Now let's write our model, right? So let's go ahead and write our model. This is going to look like every other GPT out there. So MyTorch, import mytorch.nm as nn, import numpy as np, and from data classes, import data class. So here will be the structure of the GPT model, right? The vocab size, the max sequence length, tiny little model, 6 blocks, 6 heads, nothing important. And this extra flag for use full auto. And this is how we'll toggle between the automatic mode and the non-automatic mode, so we can compare the benefits, right? Class embeddings nn.module. So the embedding, very simple, definite self, we're going to pass in this, the config from above, super.init, and this can be self.config is our config, self.car embeddings, these will be the character embeddings, will be nn.embedding, and it's going to be config.vocab size to config.embed.dim, right? That's our character embeddings. We also need positional embeddings, right? So this will be kind of the same thing, so I'll paste it in. Positional embeddings, again, are going to be some learnable parameters. We could have also done non-learnable sine, cosine embeddings, but we'll make them learnable parameters for now. Just some learnable parameters for every single position. Have an embedding vector that represents the position of the token with respect to the other tokens. And so in our forward method, def forward self input ID, so it's what they'll be, right? We can do our batch size by sequence len is input IDs.shape, right? So that's the shape of the data we're passing in. X is going to be self.car embeddings input IDs. So there's the character embeddings. And now what we're going to do is avail index. So how many samples are we passing in? Let's say the positional embedding supports up to 256 positions. We're only passing in 15 of them. So we don't need all 256. We need to index out the first 15. So avail index will be MyTorch.arange, which we implemented, from start equals 0 to end equals sequence len. .2, make sure it's on the right device, input IDs dot device. So this will be from 0 to however many tokens we have, right? And then our positional embedding is going to be self.positional embeddings avail index dot reshape. And remember, we did it here, so this will return basically a let's see, 1 by sequence len, right? That's basically what, actually it'll just return a sequence len by embed.dim, right? That's what it's going to return. For every single position that's available, we'll have an embedding dimension. We need to just add an extra 1 to the beginning because we're going to be adding it, the positional information, is something that's batch by sequence len by embed.dim, right? So we need to basically add this extra 1 here so it broadcasts, right? Broadcasts correctly. So we can do dot reshape or unsqueeze. We can do reshape 1 by sequence len by self dot self dot config dot embed.dim, right? So whatever the embedding dim is set to, that's what we need to add. We're sort of just adding this extra 1 dimension in. That's all. Okay. Let's see here. Yes, so that's good. And then we can do x is x plus pause embed, return x. And so here's kind of the key part. Maybe this actually isn't a good example to explain, so maybe I'll mention that later. There's a couple key things here, but that's fine. Well, it'll make more sense in attention. So nn.module. Attention is just like every other attention mechanism, right? So init self config super.init self.config is config. And we can do a quick assert config.embed dim config.num heads is 0. Just make sure that the embedding dimension is divisible by the number of heads so we can actually do it. And then here's the attention head information, right? The embedding dimension, the number of heads, and the head per head dimension. So we have our attention projection self.qkvproj, which is a single linear layer from self.embeddim to 3 times self.embeddim. And auto is equal to config.use full auto. This is a flag, right? Do we want to use the automatic differentiation or do we want to use the manually defined differentiation? Completely up to us. And that's something we'll test, right? So I'm just passing that flag here. And then, of course, we have the output projection, the post-attention projection. So out proj is the same thing. So I'll paste that in here. That's the output projection. We have our 2 different dropouts, right? We have our attention dropout and we have our output projection dropout. So there's the 2 dropouts that we've implemented already. And here's the important part. We need the causal mask, right? So causal mask is going to be MyTorch. It's going to be MyTorch.trill, right? So lower triangle. MyTorch.ones 1 config dot max sequence len by config max sequence len equals 0. Or I'll just paste this in. Sorry, type all that. Basically, we have a sequence length by sequence length mask. Everything is set to 1. And we add an extra dimension in for the head dimension and an extra dimension for the batch dimension. Because remember, when you do attention, it's going to be the shape of batch by num heads, so h, by sequence length, assuming we're doing self-attention. And so we've just created a mask in this shape, but kept 1s for these dimensions, so we can broadcast over them. That's totally fine. And what we've done is lower right triangle, because this is a attention mask. So we want to make sure that we have 1, 0, 0, 1, 1, 0, 1, 1, 1. We want to make sure we attend to these tokens here as the query position is greater than or equal to the key value position. But these positions are non-causal, because this is saying have the first token attend, have the first query token attend to the second key value token, or the first query token attend to the third key value token, so on and so forth. And that means you're looking into the future. But this is GPT, which means it has to be causal, so we have to do this causal mask. And so this is just creating that. The trill creates this mask right here, and then we're checking wherever it equals 0. And wherever it equals 0 is the positions we don't want to attend to, essentially. So there we go. That is our causal mask. And then what we're going to do is just do a quick, those are causal positions. So this is basically 1 for positions that are causal, 0 for positions that are not causal. From that, we can derive our causal mask pretty easily, right? So this is going to be like this. Masked fill in the zeros. Basically, wherever it's causal, go ahead and fill with negative infinity, because that's how we do attention, right? Before we do the softmax, we add negative infinity to the positions we don't want, so that post softmax, the negative infinities are basically just 0, right, as a probability, right? So in comparison to everything else. So that's it. So that's our trick. Self dot register buffer causal mask, and persistent is false. So like we mentioned, this is something we need our model to have, but we're not training it, right? These aren't learnable parameters, so we can store it as a buffer. And also when we save our model weights, we won't be today, but in the future, when we save our model weights, we don't really need to save this mask either, right? We can just create it again when we need it, when we load the model. So that's why persistent is false. We don't need to save it. For some other buffers, like for batch normalization, then you do need to save them, right? Those would be persistent is true. Okay, good. Def forward, self x, and let's do the standard batch size sequence len embed dim is x.shape. So we're doing the standard attention computation. So qkv is self.qkv proj x. QKV is equal to. So this is going to create, I'll pass the shapes in as we go. Data starts as batch by sequence length by embed dim. Now it's batch by sequence by 3 times embed dim, because that's what we set it up here. QKV is equal to QKV.reshape. It's going to be batch by batch size. And actually, let's just make this batch a bit short. Batch by sequence length. But the 3 times embed dim needs to be split up. So first what we're going to do is self.numHeads by 3 times self.headDim. So we've essentially separated the embed dim into numHeads by headDim, right? So, that's what we wanted to do. We wanted to split the embedding into multiple heads of attention, but we also have that extra 3-dimension here because we haven't split the QKV up yet. So basically for all QKV, we have this setup. We can then do QKV is equal to QKV dot transpose 1, 2. We want to transpose this dimension, and this dimension. So it's going to make it number of heads. So this will end up being batch by heads by sequence length by 3 times headDim. Just like that, 3, not 2. 3 times headDim. And then QKV is equal to torch, MyTorch dot chunk, right? We want to split it up on this dimension here. So we're going to split up QKV into 3 chunks on dim equals -1, right? And dot chunk is a operation that we've defined already that can do backprop, like so we can backprop through that. Each of them being batched by number of heads, by sequence length, by head dim, right? So that's how we've set this up. After that, we can compute our scores. That's standard attention computation. Q at k dot transpose -2 -1, right? Go ahead, qk transpose, divide by the self dot head dim to the power square root, right? Basically squared by the square root of head dim. So this is our standard attention formula. After that, we want to make sure we mask out non-causal position. So scores is equal to scores plus self dot causal mask. These positions we're broadcasting over up to the valid sequence length. So basically up to however many tokens we have. Dot as type scores dot d type. So all we're doing here, scores dot data dot d type. I don't think it matters. Yeah, it's fine. It doesn't really matter. So either way, basically we have the causal mask, but the causal mask is for all positions. But if we're only passing in 15, we only need the first 15 positions of the causal mask in each dimension. And go ahead and add those negative infinities to the scores. So all those non-causal positions, their scores are now negative infinity. Now that they're negative infinity, we can go ahead and take their softmax. Softmax attention is equal to mytorch.nn.functional dot softmax scores dim is -1, right? So there we go. I think we might have a MyTorch NN here. Let's check here. This one's fine. We have this in it. I wonder why the type thing didn't help. NN.functional. Oh, we actually haven't even added these in. 1 second. Okay, we might be chasing down some import stuff later. Let's check right here. In our model, nn.functional mytorch.nn. Okay, well, we'll see if it works or not. It might just be a VS Code thing. Either way, let's just keep going. We have our dropout, dropped attention. I'll just paste this in. We do the attention dropout, and then we just do the rest of attention, which is very straightforward. Go ahead, multiply by the V's, then go ahead and reshape back to the original batch by sequence length by embed dim shape, go through the final projection output, and then the final dropout, and we are done. The feed forward is, again, very simple. Class. Here, I can actually paste this because there's nothing fancy about this. Oh, right, the note I wanted to mention. So the cool part is AutoGrad is doing some things, but our manual differentiation is also doing some things. Because these linear layers, we've manually defined their gradients, and these softmax, we've automatically defined the gradients, but all the other operations that are happening, AutoGrad will basically take care of them. So for in most deep learning frameworks out there, these known composites of operations like softmax are highly optimized. You're not auto-gradding through softmax. We know what the derivative of softmax is. But for all the custom stuff, like everything else that you see here, those are auto-gradded through, right? We auto-grad through all of this stuff. So that's fine. So just a little thing. Feed forward, very simple. It's just two linear layers that go from embed dim to hidden size, where hidden size is the embed dim times the ratio. And then again, go from hidden size down back to embed dim, and you have some dropouts scattered through there with a ReLU activation function. After that, our transformer block is just as simple, right? It's basically just an attention layer. It's our LayerNorm, it's that feed forward, and another LayerNorm. And we just do LayerNorm x attention with the residual connection. And we just do this twice with the other feed forward. LayerNorm x, residual connection, return x, and we're done. Very simple setup. Okay. Let's see right here. Am I missing anything of importance? I don't think so. So yeah, I think we're good. Transformer block. And now we can do our BabyGPT plus BabyGPT and then dot module def init self config, and this will be very straightforward. Self dot embeddings is going to be the embeddings we implemented earlier with its config. Self.blocks is going to be nn.module list, right? So list of just a stack of these blocks. It'll be these transformer block config for blank, right? For in range config.num blocks. And so basically for every single block, just go ahead and create one of them. And then we have our final step. So we're going to do self.final layer norm. It's going to be nn.LayerNorm. It's going to be again config.embed dim to, and then auto config use full auto, right? So there we go. We have our final layer normalization after all the layers, and then we have our final prediction head, right? It's going to go from embedding dim to vocab size, right? Predict what the next token should be. Forward method is also super duper short. There we go, right? Standard forward method. Okay, good. Is there anything else? Oh, right, weight initialization. Yeah, that's fine. We can write that right here. So we're going to initialize the weights. How we typically initialize a transformer, right? We won't even bother typing this. Basically, if it's a linear layer, initialize with the normal with 0, 0.02, standard deviation, zeros for the bias. If it's embedding, same thing. If it's layer norm, then ones and zeros. This is our standard weight initialization, right? Nothing fancy. And so we can then do self.apply init weights. So the train function, let's give this a try. From model import BabyGPT, and our model is the BabyGPT. Oh, we also have the config. So we can do config is BabyGPT config, and let's see, it all starts to either come together or fall apart. We'll probably have some import errors that we'll have to deal with now. Oh. Python. Okay, let's give it a second. Oh, okay, there we go. So yeah, so you can see it's printed out quite nicely. That's that repper, right? In the module, I wrote that really annoying repper. It's just to make it look nice. It's just so it looks like PyTorch. But we can see we have our embeddings. We have all of our blocks. We have our final layer. We have our LM head for the prediction, 65, outputs because there's 65 things. And so we're good to go. I think this will just work then. So let's start implementing the actual training loop. We're going to need import numpy as np, import MyTorch. We're going to need import mytorch.nn as nn, and import mytorch.optim as optim for the optimizer. And we need our model, and we need from tqdm import tqdm for a progress bar, and from utils import prep Shakespeare and sample. There we go. So two things we're going to do. First, right, are we going to be using auto methods or manual methods? So auto grad or manual grad. And then what device do we want to train on? So that's obvious. We're also going to have some simple training parameters, right? So how many iterations, how often you want to evaluate, learning rate, batch size, how often do we want to generate a sample so we can test it, and just a starting character for that generation. So let's go ahead and load the data set. Load data. We're going to do our train set, test set, and then meta, right? The extra information will be the prep Shakespeare, and our car to index is going to be meta car to index, and our index to car, to go back the other way, is going to be meta index to car. And so now we can do our I already did that earlier, but I did it, but I can copy it back again. Load model. Our vocab size is based on whatever the meta vocab size is, and then use full auto is a flag if we want to do that or not. Our optimizer will be optim.AdamW model.parameters. So very simple, no parameter groups, just the one. Learning rate will be whatever learning rate we set. Loss function will be the nn.cross entropy loss, so that's good to go here too. And now training loop. So completed steps is 0, train is true, and our progress bar is going to be tqdm range training iterations. And so we are mostly good to go. I think we are missing one thing, and that's for the generation method. Yeah, so let's go ahead and do this. Def generate. If we actually want to generate something, right, we'll have the start index is going to be the car to index I for I in gen start. So whatever we set to here, in this case is just one letter, so that's my starting index. And then the starting tensor, start tensor, is going to be MyTorch.tensor from start index dtype MyTorch.uint32, make sure it's basically torch.long, unsqueeze 0, add a batch dimension in, .to device, make sure it's on the right GPU or wherever we're training. And for blank in range, config.max sequence length, so it should be max sequence length minus len start index, right? Because if we pass in 40 tokens, then we can only generate up to 256 right now, at least in the simple example, because we're not scanning or doing anything like that, so that's fine. And we can do with mytorch.noGrad, which is why we wrote this noGrad method. Our last logit is going to be model, right? So we're going to pass in our model, we're going to pass in the start tensor, and this is going to return something that's batch by sequence length by num characters, right? C. Now the batch dimension is going to be just 1, because we're only going to be generating one thing at a time, and we only need to predict the character for the next token. So all we need is the last S, not all of them. So we can index this out and go blank for placeholder for that, the last one, and then blank again. And we can do a quick sanity check, right, just to make sure, in case we're training in float 60. It doesn't matter, we're training in float 32, but just to make so it's compatible with everything else, we're gonna make sure it's float 32. And now what we need to do is compute our softmax, which is, we can do it however, but we can just compute our exp logits is mytorch.exp last logits minus mytorch. I guess we could just use the softmax method we already wrote, but whatever. And then probs is going to be exp logits divided by mytorch.sum exp logits. Okay, so I now have basically a vector of length 65, because there's 65 possibilities, and they add up to they add up to 1, right? The values of them add up to 1, 0.5, 0.02, whatever, right? Dot, dot, dot. And what I need to do is randomly sample a token, because that's how we typically do it. Right? We don't pick the most likely one, we just randomly sample something random, right? We need to do that. So we need to implement multinomial sampling. That's actually something we haven't done yet, but we can relatively simply. So let me just find out exactly where I save this NN. Okay, so what we need to do is implement the multinomial sampling. It's not hard, it's just a couple of little things. So what we're going to do is, it's basically called like a vectorized categorical sampler, and it essentially unrolls the probabilities so we can do our sampling. So let's just get an idea here. What we'll be passing in is this. So we're going to do def multinomial probs and num sam. How many random samples do you want to take? Typically just 1, but you can take as many as you want. Our probabilities, right? So how we're going to do it is this. Our probs, right, is going to be some dimensions, whatever it may be, and it's going to end with n classes. And it's going to return some dimension and then num samples, right? However many, that's the shape of the return. So if it's just 1, then this will just be 1. Okay, so how this is going to work is basically this. First, we need to make sure our probabilities are in float 32. This is really important because of precision errors. You'll basically end up with things that are like 1 instead of like, whatever it may be. So it's just for precision errors, that's all. Otherwise, we'll end up with, like, instead of a probability distribution adding up to 1, it's going to add up to like 0.99995 or something. And it just throws some errors, right? So we want to make sure it's that. So that's step 1. After that, we want to normalize the probabilities. We technically don't need to do this, but this is essentially assures that even if the input already is normalized, the tiny errors can accumulate. So we just want to make sure this distribution is valid. So we're going to take the probs and just divide by the sum of the probs. Again, this probs should equal to 1. So this should just be taking all the values and dividing by 1, because the sum of probabilities is always 1. But in case it's not 1, it's just something like very close to 1, just because of our loss of precision due to float 16 and stuff like that. This is why it's there. After that, we now need to actually do our cumulative density function, so CDF. And this is going to be the cumulative sum of our probs. Again, dim equals -1. So what this is doing is this. Basically, we have some probabilities that look like this, right? P0, P1, P2, P3. And I know the sum, because I've made sure of it. All of this should add up to 1. The cumulative density function will look like this, right? So the first sample, the first one's going to be P0, the next one's going to be P0 plus P1, the next one's going to be P0 plus P1 plus P2, and the third one's going to be sum of all of them, which should be, again, 1. And so this kind of defines an interval, right? So let's put in actual numbers here. Let's say 0.1, 0.2, 0.4, and 0.3. So I'm saying that the first element, I want it 10% of the time. The second element, 20% of the time. Third element, 40% of the time. Fourth element, 30% of the time. And of course, all of them add up to 1. This means this is going to be 0.1. The next one's going to be 0.3, because 0.1 plus 0.2. The next one's going to be 0.3 plus 0.4. It's going to be 0.7. Oops, 7. And the last one's going to be 1. And so now I know that if I randomly select a value between 0 and 1, if I'm between 0 and 0.1, well, that's my 10%. If I randomly select a value between 0.1 and 0.3, well, that's 20%. That's my 20% here. If I randomly select a value between 0.3 and 0.7, well, there's a 40% gap there. So there's my 40%. And again, if I randomly pick a value between 0.7 and 1, well, that's my 30%, right? So that's my 30% gap. So essentially, all I need to do is randomly sample a value between 0 and 1 and see which interval it falls in. And that interval will tell me exactly what I need of what is my sample, right? What is the thing we randomly sample? As a sanity check, we're just going to do assert CDF. There might be other dimensions. It's fine. We can ignore those. This should equal to 1.0, right? Because the sum of the CDF should add up to 1 because we've adjusted for it here. Now, we're going to randomly sample some numbers between 0 and 1, rand. And what we're going to do is there's going to be, it's going to be in the shape of probs.shape, everything but the last dimension. So basically for every single other dimension, whatever there may be here, we want to sample however many samples we want, num samples, number of numbers. And it's going to generate basically numbers between 0 and 1. And after we do that, we just need to essentially just add an extra, make sure it's on the right device first. So device is equal to probs.device. And then we're going to do unsqueeze -1, just add an extra dimension at the end. So the main things here is this, basically the shape of it is going to be kind of like this num sample, basically all the dimensions you had, num samples by 1. And now what we're going to do is check against the CDF. We're going to do sampled is equal to the u greater than CDF dot unsqueeze -2 dim equals, we don't have the dim right yet, so let's do that. So what this is doing is checking u is all of these dimensions by 1. Our CDF dot unsqueezed will be of this shape, right? So this here, and then we just added unsqueeze -2. And so actually, no, it'll be this right here. There you go. 1 by n classes. And now it's just a numpy operation, right? It's just a numpy operation because essentially we're checking, is every element in a num samples by 1 greater or less than every element in a 1 by n classes. That's basically the operation we're checking. And so in the end, basically this operation will end us with something that looks like this. It's just going to be a num samples by n classes square, right? Or not square, but matrix, right? Matrix, just like that. And that's basically it, right? That's the main idea. It just basically gives for every single sample, is it greater than the specific class or not? And whichever one it's greater than is 1, and whichever one it's not greater than is false. So what you'll end up with is something like this. So let me paste this example. Let's say we do this here. And then we basically are checking, we're doing NumPy broadcasting to make it happen. But what we're checking is, let's say we generate a random number like 0.4. If we generate 0.4, then is 0.4 greater than 0.2? Yeah, it is. Is 0.4 greater than 0.5? No, no, no. This means when I sum this together, I get a 1 plus 0 plus 0 plus 0. And this is just going to give 1. So we've essentially indexed 1 here. We've selected this one. What if I pick 0.6? Then 0.2 is true. 0.5, yeah, I'm greater than 0.5, so that's true. But I'm not greater than 0.8 or 1. So now I've selected, if I add all this together, it'll be 1 plus 1 plus 0 plus 0, which is 2. So now I've sampled the second one. If I pick 0.9, then I'll get true for the first 3 things, right? 0, true for the first 3 things. And basically, all 3 of these are true, so I'll get 3. And that's basically how the sampling is happening. And as long as I fall greater, basically which region am I falling in, and I just add those indexes up. Nothing too crazy. It's just a little fun indexing issues. So we can do a sum. Axis equals minus 1. We're going to do this along every single num sample num classes thing. Basically, for every single time we want to sample, we're going to add them up and then see how many things are we greater than, and however many things we're greater than is what we've randomly selected as our index for sampling. Good. So that is our sampling process. And we can then return sample. So that was a little extra thing we needed to do, but now we have it. Let me make sure. Yeah. Good. Back to train. Now let's wrap this up. So now that we have our probabilities, right, we can go ahead and do our next ID is going to be multinomial probs num samples is 1. 0, right, because we don't need the batch dimension. Convert to NumPy and just grab the index, right, the value itself. And that's it. So the next ID is just going to, we're just randomly sampling from this probability distribution, 1 sample, and that's going to be the next ID. And now that we have the next ID right here, we can go ahead and append it on. So it's going to be start index.append next ID, and then our start tensor, the thing we're going to actually pass into the model, we can replace it, right? Our start tensor, and then we just repeat this over and over again. We basically append, convert to a new tensor, append, and then predict a new next token, and just do it over and over and over again until we are done. Return, start, index. And that's our quick generate function. So let's go ahead and wrap this up now. The rest of this is very easy. While train inputs is going to be that sample method from our train set, right? Train set. And we'll do config.max sequence length. And we're going to do it for blank in range match size. So basically just keep grabbing chunks of whatever the sequence length is, and however many we want is the batch size. And then X, let's go ahead. So these are going to be each NP arrays, NumPy arrays. So let's go ahead and concatenate it all together, because it's a list of NumPy arrays essentially right now. It's going to be equal to np.array, I, 0 for I in inputs. And we're going to repeat that for Y as well, right? We have X and Y. Except, remember, each of these samples will return, if we look in Utils again, it's going to return an X and a Y. So we have I0 is going to be the X's that are returned in those tuples, and then I1 will be the Y's that are returned in those tuples. So X and Y. X is then MyTorch.tensor. X dtype is MyTorch.uint32.2 device, right? Make sure it's on the correct GPU, and then we do exactly the same thing with Y. And now we're done. So our output is equal to model X. Those are our logits. Our loss is the loss function between output and y. Y is our targets. After we have that, we can do our loss.backward, compute all the gradients, optimizer.step, go ahead and update our model parameters, and then optimizer.0 grad, just like how we do in PyTorch, right? And after we've done that, we can do completed steps plus equals 1 and pbar.update 1. Now that we've done that, we can go ahead and do our evaluation, which will look identical, right? Evaluation, every eval interval, throw the model into evaluation mode. At the end, throw the model into training mode, and this should be test set. I just go ahead and inference on the evaluation data. So grab the data, same way, pass it through with no grad, and then, oh, I clicked out, and then go ahead and grab your eval loss and just print them out for every kind of evaluation interval, just so we can see how things are going. If completed step, %geniter is 0, or completed steps is 1. So completed steps will be 1 right at the beginning, so we can go ahead and try it there because we update right here. So right at the beginning, just generate something. Otherwise, every generation iteration, just go ahead and generate. We do model.eval. Gen tokens is equal to generate. Go ahead and use the generation method. Throw the model back into training mode. And then we can go ahead and print those generations out. So I'll just put that right here. Right. We have to essentially take those indexes that we predicted, go index to character, get them as characters, and then just join them all back together, and then just print it out. And then at the end, we're done, right? If enough steps, we're done. Generation, we're done. So that's it. So we can go ahead and print the final generation out right at the end. And let's give this a try. It'll give us a chance to start debugging. Oh, I spelled it wrong. Multinomial. Okay, yeah, there we go. So yeah, models training, we'll see the loss probably decrease some amount. You can see initially the generation is just garbage, right? So let's see if it actually learns something of interest. We can see we're getting about 19 iterations per second. Not so bad given how reasonably small this model is, but it's not good enough, as for a lot of different reasons that we'll talk about later. Yeah, we can see the loss is decreasing. 2.3, 2.2. Let's just give this the minute. While it's running, we can open up NVTop. Only the first GPU is being used, so you can see it's using about 4 gigabytes of memory, right? So this is OBS in the monitor and stuff, so ignore that. So it's mostly just this, right? So we can see it's using about 4 gigabytes of memory, which isn't bad, but also a little bit sad for a model this small. We can start to see that the text is starting to look a little bit more like text, right? Starting to look a little bit more like words. But we can see the loss is 1.3, 2.2, 1.93, 1.75. So the loss is decreasing, 1.5. We can see it's also starting to overfit. Obviously, we can see like there's a little bit of a divergence here. We'll let it keep going here. Yeah, so this is kind of proving that, okay, looks like we have a system that's working, right? It's a system that's able to learn something. Whether or not it's meaningful is left to be seen, but it's obviously not good enough, right? There's still a lot of stuff that we've done. The goal here today was just to build a super baby GPT model based on the MyTorch AutoGrad system that we have built, and just by implementing some of these super basic layers. Okay, it looks like it's a little bit more starting to see actual words start to appear now. Width to bowling, brage for Henrying, less I short those. That hold cover Mary, that quitted. Either way, it's gonna just keep going. It's gonna do its thing. But yeah, we can see it's looking like English, which is exactly what we were expecting from a tiny little model like this. Now, for the main limitations, the entire system we have built right now is basically built on top of the AutoGrad system, and then we've gone ahead and for some of these known composites of operations, we've implemented these we implemented the backward pass. Like, we're not actually backpropagating through Softmax. We're just backpropagating because we know the formula for Softmax. We know exactly the derivatives. Okay, yeah, this looks good, right? What the mad, not the therein and the kings unto whatever it may be. This looks like English, right? It looks like English, not so bad. But we're getting about 20 iterations per second. Okay, let's try this. Let's turn auto to, I closed it. Go back here, train. Let's set auto to true. So use the full autograd system. Give it a second. It should be a little bit slower, right? So we can see it's about 16, 17 iterations per second, maybe 18, rather than 19 to 20. So we're taking a performance hit because we have to backpropagate through all of these extra operations. And the difference might seem a little bit not so meaningful right now, but once we start scaling the model up, then it becomes more of a challenge. And that was kind of the main point I want you to take away from this video. The problem becomes this. We have currently, we're using first of all, actually, that was a good test. Let's do auto is true again, because we remember it was using about 4 GB of memory earlier. When auto is not true, let's give that a second. Let it start training. We can see our memory cost actually we'll give it a second for it to catch up. Auto is true. Oh, maybe it's not true. Okay, yeah. We can see the memory cost actually starts to spike if we give it a little bit of time for it to start caching. We can see it's actually 4.66. So our memory cost is slightly higher because it has to store those intermediate computations, right? The intermediate tensors for us to backpropagate through these things have to be stored, and it just slows everything down a little bit, right? So we can see it's a little bit slower and that sort of stuff. That's problem number 1. Problem number 2 is this, and this is the main one. What happens if we scale our model up? The model that we've defined here is super, super tiny, right? It basically has no parameters in it. I think it has about 10 million parameters in it. It's nothing. But what if I want to scale this up to 125 million parameters, like the official GPT implementation, or the 1 billion parameter LLM that I've already trained with the MyTorch system? How do I get it there? Because if I want to make this bigger, like let's make it a reasonable LLM, we have a 50,000 vocab size. We have an embedding of 768. We have a sequence length of 1024. We have 12 blocks and 12 blocks. And this is kind of the standard size or shape of a GPT model. If I attempt to train this model right now, you'll see exactly the problem. We'll get a huge spike in memory and then it crashes. We get the CUDA out of memory error. So what we've written right now is reasonable, but it's not good at large models. And the main penalty is this. If we reduce the sequence length to 256 again, this should train, albeit slowly, but it will train. We can see it's using much less memory, right? So you can see it's only using 9 GB, which is nice. And it's training at a reasonable speed, despite the model being so big, right? Despite it being so big. And we could probably scale the model even more and get away with it. And this is, again, at float 32 precision. So here is the plan. The main penalty we're paying is attention is quadratic. So there are a bunch of stuff that we're going to have to do to pull this off. Let's go. Let me pull up my right here. We have some modules. We have some custom operations, which is kind of like attention and stuff like that. And then we have known composites. We've defined a bunch of manual operations for things that we need, but this is not enough. We now need to start writing fused kernels because they're faster, and we can make them significantly less memory intensive for large tensor processing. This means we need to essentially work our way up to writing the flash attention kernel. The flash attention kernel. So on my Git repo, you'll already find flash attention implemented because I have already implemented this. So this is basically a repo similar to NanoChat from Karpathy using MyTorch instead of PyTorch. And in this one, I have been able to successfully train a 1 billion parameter LLM, right? So I'm still testing and getting all of this to kind of work out nicely, but this system has been able to train that. To pull this off, right? To pull all this off, we just need to essentially do a bunch of little things to keep track. The main things essentially being we need fused kernels. We need to write a whole slew of fused kernels. So in our MyTorch, in nnet, and then fused ops, where are they? Functional fused ops, you can see there's a bunch of fused kernels. We need to go back and rewrite them for everything. We need a layer normalization fused kernel, a activation functions fused kernels. We need our embeddings fused. We need cross entropy fused. We need our most important, and this will be the toughest one, flash attention fused. This will be probably the most complete example. There's a couple of implementations on YouTube right now that you can go watch. As far as I know, none of them support things like group query attention and some of the other stuff that you'll find on modern LLMs. So we're going to be implementing those things as well, right? So it'll be basically a full-on attention implementation that's supposed to be pretty close to the torch.sdpa, right? You can take a look at these videos here or Git repos that are also great tutorials. So that's phase one. We need to write kernels, but writing kernels is not enough. The other penalty we're paying is float 32 precision. Float 32 precision is not how we typically train neural networks these days. The most standard format is actually training in BF16, BrainFloat 16. BF16 is awesome because it gives you the dynamic range of float 32, but at the precision type, the memory consumption of float 16. Unfortunately, CuPy, which is our backbone for GPU, for all the GPU operations, does not actually support BrainFloat 16, BF16, for some reason. CuPy tries to be as close to NumPy as possible, and NumPy obviously won't support BF16 because, well, NumPy is for CPUs and BF16 is for GPUs, which is a little unfortunate, but it makes us work a little bit harder. So we need to write a couple other things for a full pipeline. We need to write a mixed precision training on float 16, but also DDP training on multiple GPUs. This we can do with CuPy. So these are the things we'll be focusing on next. I haven't decided the exact order in which we're going to do it. We're most likely going to start with the kernels. We're going to start with some introduction to like how do you write Triton kernels, because Triton kernels are way more convenient to write than CUDA kernels. So we're going to start with that. And once we have the baselines down for Triton kernels with like a simple vector sum and then matrix multiplication operation, we're just going to like every single video is just going to knock out one of the Triton kernels, and we're going to work our way up to the flash attention, which will be the hardest one. Once we have all those kernels written, we'll come back and then write probably the mixed precision and DDP training after that. This is going to look like the Accelerate, like Hugging Face Accelerate. I love Hugging Face Accelerate. I use it for all of my training, all of my research. So we're going to write an API that's essentially identical to Hugging Face Accelerate. We're going to build our own Accelerate, which is going to be awesome. Once all that's done, then we're going to essentially go ahead and reproduce the GPT-2 model. And then we're going to train a full LLM. So we're going to basically go through the NanoChat pipeline of pre-training on 10 billion tokens of the Hugging Face dataset. I forgot what it's called right now. What was it called? The Hugging Face Smalltalk. This was trained on... No, Smalltalk was a synthetic SFT dataset. Okay, either way, I can't remember the exact name. Oh, it's called FineWeb. There we go. So we're going to train on the FineWeb dataset, 10 billion tokens of that, or 100 billion for the 1 billion parameter model, or whatever it was. I can't remember. 20 billion tokens for that. We're going to train on FineWeb, then we're going to do mid-training on conversational data, supervised fine-tuning on conversational data. And that's as far as I've gotten so far. I want to include an example of reinforcement learning with MyTorch as well, probably GRPL or something like that. I just haven't gotten there yet, but that's kind of less important for the purposes of what we're trying to do. But again, the whole goal is we want to build a fully functional deep learning framework that's not just a toy. So our next video will be an intro to Triton for vector summation. So I will see y'all in the next one.